In 2022, humanity opened a new window into the deep past. That's when the James Webb Space Telescope sent back its first images, stunning, detailed, and far older than anything we'd ever seen. With its powerful infrared vision, JWST looks back over 13 billion years, capturing the faint light from the earliest stars and galaxies. For generations, the birth of the universe has been one of the biggest mysteries. But now, for the first time, we're beginning to see it unfold, and what we're discovering is shaking up everything we thought we knew about how the universe began. Before we start today's journey, let us know where in the world you're watching from, and what time it is for you right now. Post it in the comments below, and settle in for a fascinating ride to discover what the James Webb Telescope found at the edge of the universe. In the first few moments after the Big Bang, the universe was like a boiling sea of energy and tiny particles, moving wildly with no order. It was so hot, trillions of degrees, that even atoms couldn't form, let alone stars or planets. For hundreds of millions of years, the universe stayed in this thick, glowing state as it slowly expanded and cooled down. Then, about 400 million years after the Big Bang, something amazing happened. The first atoms joined together to create hydrogen and helium, the basic gases that stars are made from. Gravity pulled these gases together, and the first stars were born. These stars gathered into the earliest galaxies, lighting up a universe that had been dark for so long. This incredible time is called the cosmic dawn, and that's exactly what the James Webb Space Telescope is now observing. It's capturing light and information from when the very first galaxies began to shine, helping scientists uncover the secrets of our distant past. The James Webb Space Telescope is unlike any other telescope we've ever built. It was launched on December 25, 2021, and now it orbits the Sun at a special spot called the Second Lagrange Point, or L2. This location is about 1 million miles from Earth and is perfect for keeping the telescope stable and cool. Being so far away also keeps it free from the Earth's heat and brightness, allowing it to get a clear view of space. What makes JWST especially powerful is its ability to see infrared light. Most telescopes use visible light, but infrared can pass through clouds of gas and dust, revealing hidden stars and galaxies we couldn't see before. Even more important, infrared light helps JWST see the oldest stars and galaxies in the universe. As the universe expands, light from faraway objects stretches into longer wavelengths, shifting from visible light to infrared. This is called cosmological redshift. The farther away something is, the more its light is stretched. Because JWST is built to detect these faint, stretched-out signals, it can look deeper into space and further back in time than ever before. It's almost like a time machine, showing us the universe as it was more than 13 billion and 500 million years ago, just a few hundred million years after the Big Bang. So, JWST isn't just taking beautiful pictures, it's helping us learn how stars were born, how galaxies formed, and how everything we see today began. When JWST sent back its first images, scientists were amazed. It had looked deep into space and captured something incredible. Galaxies forming just a few hundred million years after the Big Bang. At that time, the universe was still very young, yet what JWST showed was a sky full of action. Scientists had expected to see only a few small galaxies, but instead, they saw many, more than they ever imagined. These galaxies came in all sorts of unexpected shapes and sizes, which suggests the early universe was much more active and full of surprises than we thought. One of the biggest discoveries was the detection of protogalaxies, the first small groups of stars that later came together to form the massive galaxies we see today. These early galaxies were not neat and smooth like the spiral or round galaxies we now know. They were messy, uneven, and wild. Stars were being born at incredible speeds, bursting into life in huge numbers. This changed how scientists think about galaxy formation. It turns out that galaxies didn't form slowly and quietly. They were born in a rush, during a very chaotic time. But JWST didn't stop there. It's also finding signs of the universe's very first stars, known as population 3 stars. These were totally different from the stars we see today. They formed from the simplest materials, mainly hydrogen and helium, left over from the Big Bang. They had no heavier elements like carbon or iron. Scientists think these stars were enormous, much bigger than our Sun, and they burned very hot and bright. Because they lacked heavy elements, they used up their fuel quickly and lived short, dramatic lives. When they exploded, they created supernova blasts, some of the most powerful explosions in the universe. These blasts scattered the first heavy elements into space, which later helped form new stars, planets, and even life. By finding signs of these long-lost stars, JWST is helping scientists figure out how the universe changed from a simple place into the rich and complex one we live in now. Another major breakthrough made by JWST is its ability to help us study two of the universe's biggest mysteries, dark matter and dark energy. These strange, invisible things make up about 95% of the entire universe, but we still don't fully understand them. Dark matter doesn't give off light or energy, so we can't see it directly. But JWST helps scientists figure out where it is by watching how it bends and distorts the light from galaxies behind it. This effect is called gravitational lensing, and it lets astronomers map out where dark matter might be hiding and how it affects the way galaxies grow and change. You can think of dark matter as the invisible bones that shape the universe. Then there's dark energy, the mysterious force that's making the universe expand faster and faster. By using JWST to measure how quickly galaxies are moving away from us, scientists are gathering important clues about how dark energy works. This could help us answer one of the biggest questions in science. Will the universe keep expanding forever, slow down, or one day collapse back in on itself? JWST isn't only looking at the past, it's also searching for signs of life beyond Earth. One of its most exciting jobs is studying exoplanets, planets that orbit stars outside our solar system. Some of these distant worlds might have the right conditions for life. JWST can examine the gases in their atmospheres and look for clues. If it finds water vapour, that could mean clouds and maybe even rain. If it finds methane, scientists will wonder if it comes from volcanoes or from tiny living things. And if JWST finds oxygen in large amounts, it might mean plants or other life forms are producing it. If we ever confirm that life exists beyond Earth, it would completely change how we see the universe and our place in it. One of the most surprising discoveries made by the James Webb Space Telescope, or JWST, has to do with the giant black holes found deep inside some of the oldest galaxies in the universe. These galaxies formed only a few 100 million years after the Big Bang, about 13 billion years ago. Based on what scientists currently understand, black holes that young shouldn't be very big yet. There simply hasn't been enough time for them to grow to enormous sizes, but JWST has revealed something puzzling. Some of these black holes are already incredibly massive, far larger than they should be for their age. This unexpected finding has left scientists scratching their heads. It suggests that black holes may not grow slowly over billions of years, as once believed. Instead, they might form and expand much faster than any current theory explains. This discovery is forcing astronomers to rethink the very basics of how black holes are born and how they change over time. It challenges many of the long-standing ideas about what the early universe was like, and reminds us that the cosmos is still full of mysteries waiting to be solved. Thanks to the James Webb Space Telescope, we are just beginning to uncover them. To truly understand how such astonishing discoveries are possible, we need to take a closer look at the telescope itself. The James Webb Space Telescope is a masterpiece of modern science and engineering. At the heart of this incredible machine is a huge mirror, coated in a thin layer of gold and stretching more than 21 feet wide. This mirror is specially designed to catch the faint invisible light known as infrared, light that has been travelling across space for billions of years. But the mirror isn't just one big round piece. It's made up of 18 golden hexagons that unfolded one by one like a giant metal flower blooming in space. When they locked into place, they formed a breathtaking honeycomb pattern, strong and delicate at the same time. This clever design lets the telescope gather as much light as possible from some of the most distant and ancient objects in the universe, and that's only the beginning. The JWST also carries a powerful set of tools, advanced cameras and instruments called spectrographs, that can look deeper into the universe than ever before. These tools don't just take pictures, they break down the light from stars and galaxies into its individual colours, like a rainbow. By doing this, scientists can learn what these stars are made of, how fast they're moving, and how far away they are. It's almost like doing a cosmic version of archaeology, digging through layers of light instead of Earth, uncovering secrets that have been buried in time for billions of years. But JWST is not just a brilliant piece of machinery, it's also the result of an extraordinary global effort. Although NASA led the mission, it wasn't alone. The European Space Agency, also known as ESA, and the Canadian Space Agency, or CSA, made major contributions. ESA provided important scientific instruments, and CSA added cutting-edge technology and helped fund the project. Together, these space agencies turned a dream into reality. The James Webb Space Telescope is a shining example of what the world can accomplish when countries come together with a shared goal: to better understand the universe we all live in. Thanks to this international teamwork, the JWST has already started changing how we see the cosmos. And what's even more exciting, this is just the beginning. The telescope is expected to keep sending back valuable information for many years to come. Every new discovery will spark more questions, inspire more research, and encourage a new generation of scientists to reach for the stars, literally. And JWST is not the only mission on the horizon. More amazing tools are on the way. The Nancy Grace Roman Space Telescope, for example, will help us look even deeper into the mysteries of dark energy and dark matter. The European Extremely Large Telescope, which will sit high in the Chilean mountains, will offer even sharper images of faraway galaxies and stars. These new observatories, working alongside JWST, will help build an even clearer picture of the universe, from how it began to where it might be heading. These discoveries are about more than just science. They're about connection. They link us to the very beginning of time, to the stars that created the elements in our bodies, and to the ancient galaxies that shine like tiny sparks in the vast darkness. They remind us that we are part of something much greater, something beautiful and mysterious. By looking back in time more than 13.5 billion years, the James Webb Space Telescope lets us witness the birth of the cosmos itself. The universe is unbelievably huge, and for hundreds of years scientists have been trying to uncover its mysteries. They've asked big questions, like where did everything begin? How did it all start? And how has the universe changed over time? One of the most mysterious and important clues in this cosmic investigation is something called redshift. This strange effect helps scientists understand how the universe has been stretching and expanding ever since it first came into existence. To really understand what redshift is, we need to go back to something simple: light. Light travels in waves, kind of like the ripples that spread out when you toss a pebble into a pond. These waves can be short or long, and each size or wavelength shows up as a different colour. For example, shorter wavelengths make light look blue, while longer ones appear red. When scientists study light coming from stars, galaxies, and other objects in space, they can measure the wavelength to learn more about where that light came from. Now here's where redshift comes in. Redshift happens when the light's wavelength gets stretched, so instead of looking blue or normal, the light shifts toward the red part of the spectrum. Think about the sound of a car zooming past you. As it gets closer, the sound is higher. But as it drives away, the sound drops and becomes lower. That's called the Doppler effect. Light behaves in a similar way. When an object in space moves away from us, the light waves it gives off get stretched out. That stretched light appears more red than usual. That's redshift. In outer space, when galaxies or stars are moving away from Earth, the light they send us gets stretched, causing redshift. The faster something is moving away, the more its light is stretched and the stronger the redshift becomes. This shift is a powerful tool. By measuring redshift, scientists can figure out how fast a galaxy is moving and how far away it is. Redshift has helped us understand that the universe isn't still. It's growing larger all the time. The idea of redshift is closely tied to one of the most important discoveries in astronomy. Back in the 1920s, an American astronomer named Edwin Hubble was studying distant galaxies. He made an amazing discovery. These galaxies weren't just sitting still, they were moving away from Earth. And even more surprising, the farther away a galaxy was, the faster it seemed to be moving. This pattern became known as Hubble's law, which tells us that the universe is expanding and that galaxies farther from us are racing away at higher speeds. This discovery gave scientists one of their strongest clues that the universe began with a huge event called the Big Bang. According to the Big Bang theory, the universe started as a tiny, extremely hot and dense point about 13.8 billion years ago. Since that moment, it has been stretching and expanding in all directions. As galaxies move away from us, the light they send gets stretched out too, so we see it as redshift. By looking at how much the light from a galaxy has shifted, astronomers can guess how far away it is. The more the light is redshifted, the faster the galaxy is moving and the farther away it must be. So when we look at redshifted light, we're not just seeing where a galaxy is, we're actually looking into the past. That's because light from faraway galaxies takes a very long time to reach us. The more redshifted the light, the longer it has travelled, and the farther back in time we're looking. Now here's something really exciting. Redshift doesn't just help us understand how fast galaxies are moving, it also gives us a chance to see the universe as it was billions of years ago. When we look at very distant galaxies, we're seeing them as they were a long, long time ago because their light has been travelling through space for over 13 billion years. That means we're seeing these galaxies not as they are today, but as they were when the universe was still young and just beginning to grow. The deeper we look into space, the farther back in time we go. The galaxies with the highest redshifts are the ones that are the farthest away from us, and that means they are also the oldest ones we can observe. These galaxies formed only a few 100 million years after the Big Bang. Studying them helps scientists learn how the first stars and galaxies were born. It's almost like peeling back the layers of time to witness the universe growing up, starting as a small, hot and crowded place, and slowly becoming the vast, star-filled cosmos we know today. These high redshift galaxies are like cosmic time machines. They offer rare and precious views into the universe's earliest days. To study them, astronomers use powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope. These instruments are specially built to detect the faint light from galaxies that are billions of light years away. When astronomers examine the light from these galaxies, they can measure exactly how much it has been stretched. The more the light is stretched, the older it is, and the farther away the galaxy must be. This stretching happens because the universe has been expanding ever since the light left those galaxies. So when we look far out into space, we're also looking far back in time. That's how scientists can study galaxies that formed just a few 100 million years after the Big Bang, when the universe was still a baby. Now, how are these early galaxies different from the ones we see today? Well, galaxies from the early universe were much smaller and messier. They hadn't had time to grow into the large, well-formed galaxies we see in our modern skies. Instead, they were still busy forming new stars and pulling in gas. These baby galaxies were often lumpy, irregular, and not very organised. They didn't have the neat spiral shapes or smooth curves we associate with mature galaxies. In those early times, galaxies were also crashing into each other and merging. These cosmic collisions were actually very important. They helped shape the galaxies and sparked bursts of star formation. Without those chaotic early mergers, we wouldn't have the beautiful, complex galaxies we see today. So, by looking at galaxies with high redshifts, astronomers can travel back billions of years to see how the universe began, how the first stars and galaxies were born, and how everything grew from a tiny, fiery beginning into the grand, sprawling universe we live in now. One of the most exciting things about studying galaxies that are very far away, what scientists call high redshift galaxies, is that they give us a rare glimpse into the time when the very first stars in the universe were born. These stars are called population 3 stars, and they likely formed not long after the Big Bang, which happened around 13.8 billion years ago. Back then, the universe was still very young and mostly filled with just two basic gases, hydrogen and helium. As time passed, gravity slowly pulled these gases together. Over millions of years, they clumped up, got heavier, and eventually collapsed in on themselves, lighting up for the first time to create the very first stars and galaxies. But these early stars were very different from the ones we see in the night sky today. They were much more massive, they burned hotter, and they used up their fuel much faster. Unlike today's stars, which contain a mix of elements like carbon, oxygen, and nitrogen, these ancient stars were made almost entirely of hydrogen and helium. They had none of the heavier elements that are so important for creating life. When these massive stars reached the end of their lives, they exploded in huge supernova blasts. These explosions released a tremendous amount of energy and created heavier elements, like carbon, oxygen, and iron. These new elements then spread out into space and eventually became the building blocks for new stars, planets, and even life itself. The lives and deaths of these first stars were some of the most important moments in the history of the universe. They helped shape everything that came afterward, setting the stage for the complex universe we see today, full of stars, galaxies, and living things. By studying galaxies that are extremely far away, scientists are learning more about these early stars and how they changed the universe forever. These ancient stars also played a leading role during a crucial time called the Epoch of Reionization, which happened several 100 million years after the Big Bang. At that time, the universe was dark and filled with a thick fog of gas. But as the first stars began to shine, their powerful light interacted with the gas and caused it to become ionized, meaning the atoms were stripped of their electrons. This changed everything. Suddenly, light could move more freely across the universe, making it transparent and allowing us to see farther into space. This moment marked the beginning of the bright, open universe we know today. Now, how do we see these ancient stars and galaxies if they're so far away in time? That's where redshift comes in. Redshift isn't like science fiction time travel. No one is jumping into a time machine. Instead, it's a scientific way of looking back in time using light. When we look deep into space, we're actually seeing light that left those distant galaxies millions or even billions of years ago. Because the universe has been expanding since the Big Bang, this ancient light gets stretched out as it travels, making it appear more red, hence the name redshift. The farther away the galaxy, the more its light has shifted and the older the image we see. So, by studying redshifted galaxies, astronomers are actually looking back in time. It's like watching a cosmic movie in reverse, seeing how the universe looked when it was much younger. This light acts like a message from the past, carrying with it clues about how stars and galaxies formed, how the universe changed, and even how it might continue to evolve. When we look at galaxies like Andromeda, which is more than 2 million light-years away, or even farther, we're seeing them as they were millions or billions of years ago. That means the light reaching our eyes today has been travelling through space since long before humans existed. It's a powerful reminder of just how vast the universe is and how small we are in comparison. Redshift gives scientists one of the best tools for unlocking the secrets of the early universe. With every new discovery, we move closer to answering some of the biggest questions. How did the first stars and galaxies form? When did black holes begin to grow? Could there be life on other planets, or even signs of alien civilizations waiting to be found? In the coming few decades, scientists expect to learn even more by using advanced telescopes and instruments. These tools might help us find the first black holes, understand how galaxies grew over time, and maybe even detect signs of life beyond Earth. Redshift is more than just a shift in colour. It's like a time machine made of light. It helps us see back to the very beginning of the universe. These distant galaxies act like time capsules, holding the secrets of creation inside them. By studying their light, we get to witness the birth of stars, the forming of galaxies, and the unfolding of cosmic history. Galaxies are gigantic groups of stars, gas, dust, and something mysterious called dark matter. All of these things are held together by gravity, the same force that keeps our feet on the ground. Galaxies come in different shapes and sizes. Some, like our own Milky Way, are spiral-shaped, with long arms that swirl out like a pinwheel. Others are more like big, smooth balls. These are called elliptical galaxies, and they usually contain older stars. Then there are irregular galaxies, which don't have any clear shape. These often got their strange forms because they crashed into other galaxies in the past. Galaxies aren't just floating around randomly in space, they're the building blocks of the entire universe. Inside galaxies, stars are born, shine for millions or even billions of years, and then die, sometimes in huge explosions. These dramatic endings help shape what the galaxy becomes. Galaxies are also where planets, like Earth, are found. They hold everything we know: asteroids, comets, planets, stars, and dark matter too. Galaxies can be very different in size. Some are small and have only a few billion stars. Others are enormous, containing hundreds of billions or even trillions of stars. Our Milky Way is somewhere in the middle, with about 200 billion stars. And the universe is filled with galaxies. There are billions of them that we can see. Each one has its own unique story to tell, giving us clues about how the universe was born and how it has changed over time. Whether large or small, every galaxy plays an important role in the universe's history. Scientists believe that galaxies started forming a few 100 million years after the Big Bang, which is the event that began everything in the universe. The Big Bang happened about 13.8 billion years ago. Back then, the universe was very young and extremely hot. At that time, the only elements around were hydrogen and helium, the two simplest and lightest elements. As time passed, the universe started to cool down. Gravity began pulling together huge clouds of gas and dust. These clouds collapsed under their own weight, which led to the birth of the very first stars. These newborn stars then gathered into the first galaxies. These early galaxies were not like the ones we see today. They were much smaller, less complex, and made mostly of young, glowing stars. They didn't yet have the heavier elements like carbon or oxygen, but these simple early galaxies helped build the larger, more detailed galaxies we see now. Since the Big Bang, the universe has been expanding. Galaxies have been slowly drifting apart from each other, and this stretching of space hasn't stopped. In fact, it's getting faster, which is something scientists are still trying to understand. As galaxies moved and grew, they sometimes bumped into each other and merged. These galactic collisions helped create the large and beautiful structures we see in the universe today. But recently, the James Webb Space Telescope, often called JWST, made discoveries that surprised everyone. It found galaxies that formed much earlier than scientists thought was possible. This has completely changed how we think the early universe worked. One of the most surprising things JWST found was galaxies that are much older than anyone expected. Scientists had believed that the first galaxies didn't appear until around 400 to 500 million years after the Big Bang. This idea was based on the thought that the universe needed time to cool down so stars could form. But JWST found galaxies that may have formed just a few 100 million years after the Big Bang. Even more surprising, these early galaxies look well formed and full of stars. That means they must have formed very quickly, much faster than scientists ever imagined. This discovery is forcing scientists to rethink how fast the universe changed after it began. One especially amazing discovery was a galaxy that seems to have formed just 230 million years after the Big Bang. This goes against everything scientists believed about how galaxies begin. For such a galaxy to form so early, the conditions in the universe must have been very different from what we thought. It hints that something unknown, maybe the way matter clumped together or how stars were born, was happening in the early universe. These discoveries are extremely important because they show that many of our past ideas about the universe might not be right. The fast creation of these early galaxies challenges the belief that galaxy formation was a slow process. Now, scientists are wondering, what was special about the early universe? Was there something unusual going on that helped galaxies form so quickly? Could there have been strange types of dark matter or chemical mixtures we don't yet understand? JWST also found that these ancient galaxies were full of activity. They were making new stars at a fast pace. Scientists used to think that star formation in the early universe was slow because there weren't enough heavy elements like carbon or oxygen, which are needed to form stars. These elements are usually made inside older stars. But if these galaxies were already creating lots of stars, then maybe the conditions were better than we thought. Or maybe our understanding of the first stars is completely wrong. Either way, these findings are changing what we thought we knew. Some of the galaxies that JWST found are also much bigger and more complex than expected. They have organized shapes and a variety of stars inside, which is very surprising considering how young they are. Scientists once believed that galaxies in the early universe were small and simple, but these discoveries prove otherwise. These surprising finds also raise new questions about dark matter and dark energy. These two mysterious forces make up most of the universe's mass and energy, but we still don't know much about them. The new discoveries suggest that dark matter might have played a bigger role in forming galaxies than we thought, and dark energy might be affecting how fast the universe is expanding in ways we don't yet understand. All these unexpected discoveries made by the James Webb Space Telescope may completely change how scientists explain the early history of the universe. It's now clear that many of our older ideas about the universe's beginning and growth are incomplete. Scientists will need to come up with new theories to explain how ancient galaxies formed so quickly. These new findings might lead to major breakthroughs in the next few years. Scientists will likely need to rethink everything from how stars are born to how galaxies grow and evolve. These discoveries also show us that the first few 100 million years after the Big Bang, an era we still know very little about, could be full of secrets waiting to be uncovered. This surprising discovery raises many new questions about the very beginning of everything we know. Scientists are still trying to fully understand what it all means, but one thing is clear: the universe is much more mysterious and amazing than we ever thought. One of the most jaw-dropping discoveries made by astronomers comes from a galaxy known as GNZ 11. This galaxy is located an astonishing 13.4 billion light-years away from Earth. In other words, when we look at it, we're seeing it as it was just 400 million years after the Big Bang. That's incredibly early in the life of the universe. Most galaxies wouldn't have had time to grow much by then, but GNZ 11 is different. What makes GNZ 11 so surprising is its massive size. For such a young galaxy, it's far bigger than anyone expected. It holds hundreds of billions of stars, putting it in the same league as our Milky Way, which is more than 13 billion years old and has had all that time to slowly grow and evolve. Yet somehow, this baby galaxy was already huge when the universe was still in its infancy. Even more incredible is how fast GNZ 11 seemed to grow. Not only was it large, but it was also expanding at a speed that stunned scientists. Galaxies at that stage in the universe's life weren't supposed to grow this quickly. This means GNZ 11 had access to a huge amount of gas, the main ingredient for making stars, at a time when such resources were thought to be scarce. This discovery has forced scientists to completely rethink their ideas about how galaxies form and grow. GNZ 11 just doesn't fit into the old models, and GNZ 11 isn't alone. Scientists have now discovered other massive galaxies that existed in the early universe, and they're just as puzzling. These galaxies are located millions or even billions of light years away from us, and they're not only enormous, but also highly complex. Some already have spiral arms or other detailed structures. Others even have supermassive black holes sitting right in their centers. That's the kind of thing we expected to find in mature galaxies, those that had billions of years to develop. But here they are, fully formed and gigantic, when the universe was still very young. It's like finding a grown adult in a nursery. It doesn't match anything we thought we knew. The big question now is, how could these galaxies grow so fast and become so complex when the universe was just starting out? One idea scientists are exploring is something called direct collapse. Normally, galaxies grow slowly. Tiny clouds of gas come together, forming stars and slowly building a galaxy piece by piece. But with direct collapse, everything happens much faster. A giant cloud of gas can collapse all at once, forming an entire galaxy in a much shorter time. This could explain why we're seeing these giant galaxies so early. Another possibility is that the early universe was just different, more extreme, more chaotic, and more energetic than we imagined. In the first few 100 million years after the Big Bang, space was filled with thick clouds of gas, intense radiation, and lots of violent activity. This wild environment might have pushed gas into dense pockets, where it quickly turned into stars. Galaxies could have formed rapidly in this chaos much faster than they do today. Scientists also believe that something called dark matter may have played a huge role. Dark matter is a mysterious, invisible substance that doesn't emit light, but it does have gravity. That means it can pull things toward it, like gas and stars. If dark matter was clustered in certain parts of the early universe, it could have pulled in enough material to help galaxies form very quickly and grow much larger than anyone expected. Another mind-blowing discovery is that some of these early galaxies already had supermassive black holes in their centers. These black holes are millions or even billions of times heavier than our Sun. Usually black holes take billions of years to form, starting from collapsing stars. But here we are, finding these monsters in galaxies that were only a few 100 million years old. How did they grow so fast? One explanation is, again, direct collapse. Not just for galaxies, but for black holes too. Maybe huge gas clouds in the early universe didn't even bother turning into stars first. They just collapsed straight into black holes. That would skip the usual steps and allow black holes to form much faster. Another idea is that these black holes were eating enormous amounts of gas around them, growing rapidly by pulling in everything nearby. This feeding frenzy could explain why they're already so massive. These discoveries have turned old theories upside down. For decades, astronomers thought galaxies formed slowly and gradually, with stars slowly gathering together under gravity. But now, with evidence of fast-forming huge galaxies and black holes, scientists are exploring new ideas. Maybe galaxy formation didn't follow just one path. Maybe some galaxies grew slowly, while others exploded into existence almost overnight. This new view opens up fascinating possibilities. It suggests that the early universe wasn't quiet or simple. Instead, it might have been a wild and energetic time full of fast-moving changes. Galaxies could have grown, merged and transformed in a matter of millions, not billions, of years. These discoveries also raise new questions. Could dark matter have shaped the early universe even more than we thought? Could supermassive black holes have influenced how galaxies formed from the very beginning? It's starting to look like these forces, once considered side characters, might have played leading roles in shaping the cosmos. Most amazingly, these findings might even rewrite our understanding of cosmic history. If galaxies could form so fast and grow so huge right after the Big Bang, then the early universe might have evolved much more quickly and dramatically than anyone imagined. This could change how we see the so-called cosmic dark ages, a mysterious time after the Big Bang when the universe was thought to be dark and empty. Maybe it wasn't so quiet after all. Maybe it was a time of blazing stars, fast-growing galaxies, and violent black holes, an age of cosmic fireworks instead of silence. Today, when we look out into space, most of the galaxies we see fall into two main types: spiral and elliptical. Spiral galaxies, such as our own Milky Way, are easy to recognize because they look like giant pinwheels. Their long, beautiful arms swirl outward from a bright central core, and these arms are full of stars, gas, and dust, all spinning together in a graceful dance. Elliptical galaxies, on the other hand, don't have arms. They're round or oval-shaped, and their stars move in many different directions, creating a smoother and more uniform look. But when scientists look deep into space and far back in time, they find that the first galaxies were very different from the ones we see now. These ancient galaxies didn't have neat shapes. They were messy, unbalanced, and often appeared as strange blobs. It was as if the universe had not yet figured out how to make galaxies look organized. Instead, everything was still swirling, crashing, and shifting in what seemed like constant cosmic confusion. This difference has to do with how galaxies were born. In the early days of the universe, just a few 100 million years after the Big Bang, which happened about 13.8 billion years ago, galaxies were still young. They were much smaller and hadn't yet formed into neat spirals or smooth ellipses. The stars, dust, and gas that made them were scattered in clumps, often looking like they were still being pulled together by invisible forces. These early galaxies were still under construction, and the universe around them was wild and unsettled. Back then, space was full of energy and chaos. Galaxies were close together and often ran into one another. When they collided, their shapes became even more twisted and strange. It wasn't until much later, after billions of years of merging and maturing, that many galaxies began to take on the familiar shapes we know today. Scientists used to think that as galaxies got older, they would naturally become more organized and structured. But when they looked at the earliest galaxies, they were surprised. These ancient galaxies weren't neat or smooth. They were irregular and clumpy, like puzzle pieces that hadn't yet fit together. Some looked like broken shards, and others were made of multiple small galaxies that hadn't finished merging. It was a time of cosmic chaos, where gravity was still trying to bring order to the universe. But how do astronomers know what these early galaxies looked like, especially since they're so far away and formed so long ago? The answer lies in the nature of light. Light doesn't travel instantly. It takes time to move through space. The farther away an object is, the longer its light takes to reach us. So, when we observe galaxies that are billions of light years away, we are actually seeing them as they looked billions of years ago. It's like looking into a time machine. For example, if a galaxy is 1 billion light years away, the light we see from it today left that galaxy 1 billion years ago. That means we're seeing the galaxy as it was in the distant past. The farther we look, the further back in time we go. This is how scientists study the early universe, not by travelling there, but by capturing the ancient light that has been journeying toward us for billions of years. To do this, astronomers use some of the most powerful tools ever built. The Hubble Space Telescope, which was launched in the year 1990, has taken breathtaking pictures of galaxies that are incredibly far away. But an even more powerful tool arrived in the year 2021, the James Webb Space Telescope. The James Webb Space Telescope, or JWST, was specially designed to study the earliest and most distant galaxies in the universe. It can see in infrared light, which is perfect for viewing galaxies whose light has travelled so far that it has been stretched out. Thanks to this ability, JWST can capture sharper, clearer images of galaxies from the very beginning of time, and what it sees is astonishing. Many of these early galaxies are far messier and more irregular than scientists had expected. This surprising discovery has forced astronomers to rethink their ideas about how galaxies formed and evolved. One of the most fascinating clues to understanding this puzzle comes from something invisible but incredibly powerful: dark matter. Dark matter makes up about 27% of all the mass and energy in the universe. We can't see it or touch it, because it doesn't give off light or heat like stars and planets do. But we know it exists because its gravity pulls on everything around it. In the early universe, dark matter didn't spread out evenly. It formed dense clumps in some areas, like invisible knots in space. These clumps pulled in huge clouds of gas and dust. Over time, the material gathered and collapsed under its own gravity, creating stars, and eventually, galaxies. But because the dark matter was uneven, the galaxies that formed around it were also uneven, with twisted shapes and messy structures. This explains why many early galaxies look so disorganized. Another big reason for the irregular shapes of early galaxies is that they were so close to one another. The universe was much more crowded back then. Tiny galaxies drifted near each other and often crashed together. These galactic collisions didn't usually cause stars to hit each other. Stars are spaced too far apart for that. But the gas and dust between them would slam together, heating up and triggering the birth of brand new stars. These violent mergers changed the shape and behaviour of galaxies, making them even more chaotic. As time passed, these small galaxies joined together to form larger ones. These cosmic collisions played a huge role in shaping the galaxies we see today. Even now, galaxies still collide from time to time, but back in the early universe it happened much more often because galaxies were closer together. These early smash-ups were a major part of galactic evolution. There was also much more gas in the early universe, especially hydrogen and helium, the lightest and most common elements. This gas acted like star-making fuel. Because there was so much of it, galaxies could form stars quickly and in all sorts of places, not just in neat patterns. That's why early galaxies look so scattered and unorganized. In galaxies today, star formation tends to happen in calm, concentrated areas, such as the spiral arms of galaxies like the Milky Way. But long ago it was wild and unpredictable. Stars could appear almost anywhere, and they often formed in big bursts, especially after galaxy mergers. This chaotic pattern made early galaxies look even more uneven and clumpy. Another huge player in this story is something extremely powerful: supermassive black holes. At the centre of most large galaxies, including the Milky Way, lies a supermassive black hole. These are mind-boggling objects with gravity so strong that nothing, not even light, can escape once it gets too close. But these black holes don't just sit there quietly. They shape their galaxies in incredible ways. Scientists believe that even in the very early universe, supermassive black holes had already started to form. Their powerful gravity pulled in nearby gas, dust, and sometimes even entire stars. This pulling action may have made young galaxies even more turbulent and messy, preventing them from settling into nice, organised shapes. What's more, when material falls into a black hole, it heats up and releases massive amounts of energy, sometimes more energy than all the stars in the galaxy combined. Some black holes even shoot out powerful jets of particles at nearly the speed of light. These outbursts can blast through space, rearranging gas and dust and changing how stars are born. In this way, black holes may have helped shape the wild, uneven look of early galaxies. Even now, scientists are still trying to understand just how important supermassive black holes were in shaping the universe. But one thing is certain: they were not just bystanders. They were active, dramatic players in the story of galaxy formation. As billions of years passed, the universe slowly calmed down. Galaxies grew larger, settled into more stable shapes, and formed the beautiful spirals and ellipses we admire today. But by looking deep into space, and deep into time, astronomers can still witness the universe's chaotic childhood, when galaxies were wild, energetic, and bursting with possibility. For billions upon billions of years, a powerful and invisible force has been shaping the universe: gravity. This gentle but unrelenting pull has acted like a cosmic sculptor, slowly changing the way galaxies look and behave. Gravity doesn't just keep the stars and planets in place, it also brings galaxies together. Sometimes 2 or more galaxies get so close that they actually collide and merge in dramatic slow-motion events that take millions of years to unfold. When galaxies crash into one another, the stars inside them don't usually hit each other directly. This is because the stars are so far apart. Each star is like a tiny speck in a huge ocean of space. But even though the stars don't collide, their galaxies' gravitational forces stir up massive clouds of gas and dust. This stirring causes new stars to be born in great waves of activity, like fireworks lighting up the night sky. At first, these galaxy collisions create wild, chaotic shapes, twisting, stretching, and bending the galaxies into strange forms. But as time goes on, things begin to calm down. The merged galaxy starts to settle into a more peaceful and orderly shape. Some of them take on beautiful spiral arms, like our own Milky Way galaxy, while others become smooth and round, like the elegant elliptical galaxies we see across the universe. And this story is still unfolding. Even now, the universe is not finished growing and changing. Galaxies are still merging with each other, and their shapes continue to evolve. One of the most amazing examples is happening right in our cosmic neighbourhood. The Milky Way is slowly moving toward its neighbour, the Andromeda Galaxy. These 2 giants are on a collision course, and in around 4 billion years, they will come together in a breathtaking merger. Eventually, they will form a single, much larger galaxy. This shows us that the grand dance of the galaxies is far from over. The universe is still full of movement and transformation. In recent times, astronomers made a surprising discovery. The galaxies that existed in the very early days of the universe were far more chaotic and disorderly than anyone had expected. This finding has completely changed the way scientists think about how galaxies form. For a long time, it was believed that galaxies slowly grew into neat shapes over time, but now we know that the earliest galaxies were wild, irregular, and unpredictable. These strange shapes tell us that the early universe, just a few 100 million years after the Big Bang, was a much more energetic and unstable place than we imagined. The exact forces that shaped those first galaxies remain a mystery. Scientists are still trying to understand what caused them to look and act the way they did. This puzzle is one of the most exciting challenges in astronomy today. We can think of these early galaxies as the first building blocks of the universe. By carefully studying them, scientists are slowly putting together the long and complicated history of how galaxies came to be. These observations help us understand how the universe changed from a wild, stormy place filled with raw energy into the vast and structured cosmos we see today, with its graceful spirals and massive clusters of galaxies. The odd and unusual forms of these early galaxies are like clues from a cosmic detective story. They show us how galaxies are born, how they crash into each other, and how they transform over time. As our technology improves and we develop better telescopes, we'll be able to look even deeper into space and further back in time. This means we will likely discover even more secrets about how the universe began. Right now, scientists are just at the beginning of this journey. Each new discovery brings us a little bit closer to understanding the universe's past. One of the most exciting and awe-inspiring discoveries in modern astronomy is something scientists call the earliest light. This light comes from some of the very first galaxies that formed in the universe, galaxies that came into existence only 200 to 300 million years after the Big Bang. In cosmic terms, that's just moments after the universe began. This early light gives us a rare and powerful glimpse into the universe's mysterious and ancient past, into a time when the first stars were being born, lighting up the darkness of the early cosmos. In the beginning, right after the Big Bang, the universe was not filled with stars or galaxies. It was filled with a hot, dense fog made of tiny particles. These particles were everywhere, and they kept light from moving freely. The light particles, which scientists call photons, kept bouncing around, scattered in all directions by this thick cloud of matter. It was like trying to shine a flashlight in a dense fog. You could turn it on, but the light wouldn't go very far. It took hundreds of thousands of years for the universe to cool down and expand enough so that this fog could clear. Finally, the particles started coming together to form atoms, and light was no longer trapped. It could now move freely through space. This moment is one of the most important in cosmic history. It marks the birth of what we now call the cosmic microwave background, or CMB, a faint glow that still lingers across the universe to this very day. This ancient light has been travelling across space for over 13 billion years, and when we look at it, we are truly looking back in time. But there's even more. The light from the first galaxies, which appeared about 200 to 300 million years after the Big Bang, is something truly special. This starlight was among the first to shine in the universe, and it marked a turning point, a transformation from a dark, foggy cosmos into one filled with glowing stars and galaxies. Before this, the universe was like a shadowy sea of gas. But when those first stars ignited, their light began to push away the darkness, clearing the fog and filling space with a soft, brilliant glow. This moment is known as the cosmic dawn, the time when the first light broke through the shadows. What makes this discovery so important is that scientists have now been able to detect some of this ancient light. That means we are seeing light that began its journey over 13 billion years ago, long before our own Milky Way galaxy or the solar system even existed. This light holds secrets, clues about how everything we know came to be. The era of the cosmic dawn is incredibly important for understanding how the universe developed. After the Big Bang, the universe was extremely hot and chaotic. Over time, it slowly expanded and cooled down. Eventually, tiny particles came together to form stars, and stars joined into galaxies. These galaxies would go on to shape the entire structure of the universe. But actually proving when and how this all happened was a huge challenge, mostly because of one major problem: distance. The farther away a galaxy is, the longer its light takes to reach us. So, if a galaxy formed billions of years ago, its light has to travel for billions of years before we can see it. By the time it reaches us, that light has become extremely faint. It's not only dim, but it has also been stretched out as the universe itself continues to expand. This stretching causes the light to shift into the infrared part of the spectrum, which is invisible to our eyes. To detect this stretched ancient light, scientists needed incredibly powerful tools. They relied on advanced technology, including the James Webb Space Telescope, the Hubble Space Telescope, and massive telescopes on Earth that can detect infrared light. These instruments are designed to pick up signals that our eyes could never see. Thanks to this technology, scientists have been able to peer far into space and spot galaxies from the universe's earliest days. It's like using a time machine to see what the universe looked like over 13 billion years ago. One of the biggest breakthroughs came with the launch of the James Webb Space Telescope, which is specially built to detect infrared light. It allows scientists to see further and more clearly than ever before. Without telescopes like this, we wouldn't be able to spot the faint glow from those ancient galaxies. The collaboration between telescopes in space and those on the ground has been essential for uncovering the story of the early universe. This light doesn't just tell us when galaxies formed, it also reveals how fast the universe began creating structure after the Big Bang. To everyone's surprise, galaxies and stars started forming much earlier than many scientists had predicted. This changes how we think about the early universe, and how quickly it evolved from chaos into order. Even more fascinating is what this light tells us about the very first stars, known as population 3 stars. These stars are unlike any stars we see today. They were made almost entirely of hydrogen and helium, the two simplest elements created in the Big Bang. They had no heavier elements, what astronomers call metals, and because of this they burned hotter, lived shorter lives, and died in powerful explosions. These stars helped transform the early universe by releasing huge amounts of energy. That energy began to reionize the gas that filled the cosmos, turning it from a neutral fog into a clear glowing expanse where light could travel freely. The first galaxies that formed from these early stars were probably small and irregular in shape. Over time, they crashed into each other, merged, and gradually grew larger. This slow process of merging helped create the massive spiral and elliptical galaxies we see today. By studying the properties of those tiny ancient galaxies, scientists are learning how galaxies grow, evolve, and change over billions of years. This ancient light also connects us to two of the most mysterious forces in the universe, dark matter and dark energy. These invisible ingredients make up most of the universe, but we can't see or touch them. We know dark matter must exist because of its strong gravitational pull, which helps galaxies form and stick together. And we believe dark energy is the reason why the universe is expanding faster and faster over time. The light from the early universe gives us clues about how dark matter helped shape the first galaxies and influence the way the universe grew. As scientists continue to explore, they're uncovering even more ancient light, giving us a clearer picture of the universe's beginning. Every new piece of light we find adds another chapter to the story of how the cosmos came to be. It helps us understand how stars formed, how galaxies evolved, and how the grand structure of the universe took shape. What's even more amazing is that when we look at this ancient light, we are literally looking back in time. The light began its journey millions and billions of years ago, long before the Earth or our Sun existed. So when we study it, we are witnessing the birth of the universe itself. It's like watching an ancient movie that's still playing out in the sky, showing us how everything began. The discovery of galaxies that formed only 200 to 300 million years after the Big Bang is just the start of an incredible journey into the deep past of our universe. With newer and more powerful telescopes being built, scientists will be able to look even further and uncover more secrets of the early cosmos. There are still so many mysteries left to solve, and each new discovery brings us closer to answering the biggest question of all: how did everything begin? When we look toward the future, scientists are filled with excitement and curiosity. They are eager to learn even more about the first galaxies that appeared in the early universe, the very first stars that ever shone, and the powerful events that helped shape the universe into what it is today. These early times were filled with dramatic changes, and by studying them, we can begin to understand how the universe grew from something simple into the enormous and complex place we now live in. One of the most important ways scientists study these early moments is by examining ancient light. Light that was released billions of years ago from some of the oldest galaxies ever discovered. This light is like a message from the past, carrying secrets that can help us understand where everything came from. From the shining stars we see each night to our own planet and lives here on Earth, it all connects back to the birth of the universe. As we look deeper into space, we may even start to understand the invisible forces that brought time, matter, and energy into existence. One of the most exciting discoveries in modern astronomy is the detection of light from galaxies that were formed only about 200 to 300 million years after the Big Bang. Since the Big Bang happened around 13,800 million years ago, this means scientists are observing galaxies that were born when the universe was still in its infancy. This ancient light allows us to look back through time, offering a rare and precious glimpse of the universe just after it began. It is almost like looking at a baby picture of the cosmos. This discovery opens up incredible possibilities. It helps scientists study how galaxies first formed, how the first stars were born, and how invisible forces like dark matter and dark energy influenced the growth of the universe. These discoveries also help us learn more about how the universe changed over time, from a hot glowing fog to the star-filled sky we see today. Thanks to amazing advances in technology, especially with powerful tools like the James Webb Space Telescope, we now have the ability to look farther into space than ever before. This telescope acts like a giant time machine, helping us observe light that has been travelling for over 13 billion years. It allows us to explore the farthest and most ancient parts of the universe, revealing wonders that were once hidden and unknown. By studying this light from long ago, scientists are unlocking the secrets of how everything we see today — stars, planets, galaxies, and even life itself — came to be. Each new discovery brings us closer to understanding how the universe was formed, how it works, and what our place in it truly is. And as we continue to explore deeper into space, we realize just how connected everything is, and how many more mysteries remain to be solved. The more we learn, the more incredible the story of the universe becomes, and it is a story that is still unfolding. Right after the Big Bang, the universe was a messy and super hot place full of fast-moving matter and strong light. Everything was growing quickly, and tiny differences in how matter was spread out began to show up. Some spots had more stuff squeezed into them than others, and this unevenness led to something amazing: the possible birth of the first black holes, known as primordial black holes. These black holes were not like the ones we usually hear about, those that form when huge stars run out of fuel and collapse in on themselves. Primordial black holes may have come straight from space itself. They did not come from dying stars. Instead, they were created by the extreme conditions that existed in the very first moments after the Big Bang. At that time, space was not the same everywhere. Some parts were thicker with matter than others, and gravity pulled these thick areas together. If a certain part became thick enough, it could crush itself under its own pull and form a black hole, even without a star. These early black holes could have formed just tiny slices of a second after time began, making them some of the oldest things in the universe, if they are still around today. Experts think that if enough of these very old black holes were made, they could help explain dark matter, the strange, unseen stuff that makes up most of the universe's mass. Some of these black holes might have disappeared over time through a process called Hawking radiation, but others, if they were big enough, might still be floating through space today. Though we cannot see them, they could be affecting everything around them with their strong pull. Experts think that primordial black holes might have formed during the very first tiny moments after the Big Bang, when the universe was unbelievably hot and thick. In those first tiny slices of a second, small but very packed parts of space could have crushed themselves under their own powerful pull, turning into mini black holes. These were not like the huge black holes we now see in the middle of galaxies. Primordial black holes would have been very tiny, maybe even no bigger than a single proton. But even though they were small, they could still hold a huge amount of mass in a tiny space. Some experts think their mass could have ranged from that of a space rock to a small piece of Earth. If they are still out there, these ancient black holes could be hiding somewhere in the wide universe. Some ideas even say they could be a big part of dark matter, the strange stuff that makes up most of the mass in the universe, but cannot be seen with telescopes. Proving they are real could help us learn big secrets about the early universe and the basic rules that run the universe, like gravity. In the first moments after the Big Bang, the universe was super hot and packed tight, filled with a wild mix of energy, light, and tiny particles. Unlike today's huge and well-organized universe, everything back then was squeezed into a place of great heat and pressure. Back in those days, matter was not spread out evenly. Some areas were a little thicker than others because of random changes. Most of the time, these tiny changes evened out as the universe grew, but sometimes certain spots were so thick that they did not spread out. Instead, they crushed inward under their own pull. This crushing led to what experts call primordial black holes, tiny but extremely strong objects that could have been around since the start of time. These black holes were not like the ones we know today, which usually come from big stars running out of fuel and falling in on themselves. The first black holes were born from the wild conditions of the early universe. Some of them might have been as small as a single atom but packed with great energy, while others could have gotten bigger with time. If they are still around, they might help us understand more about how the early universe worked, and even give us clues about dark matter. These black holes are called primordial because experts think they were made during the very first moments of the universe, long before stars, planets, or galaxies were around. Unlike the black holes that form today from dying stars, these very old ones might have appeared in the first few seconds or minutes after the Big Bang. During that short but intense time, the universe was a hot and thick sea of energy and particles. If certain areas had just the right mix, like high pressure and thickness, gravity could have made them crush inward and form tiny but very heavy black holes. These first black holes might still be floating out there today, hiding in the wide universe. Some ideas even say they might make up part of dark matter, the strange stuff that experts think makes up most of the mass in space. Primordial black holes are a very different kind from the ones we often hear about. Most black holes are born when huge stars run out of energy and fall in on themselves. These are called stellar black holes, and they can weigh from a few times more than our Sun to many times more. But primordial black holes are thought to have formed in a totally different way, right after the Big Bang, in the early seconds of the universe. Because of this, they do not need to be big. In fact, some experts think they could be incredibly tiny, maybe as small as one atom. Even though they are so small, they would still be very heavy, squeezing a huge amount of matter into a tiny space. This makes them very interesting to scientists, because they might act very differently from the black holes we usually study. Some experts even believe these tiny but powerful black holes could help us solve some of the universe's biggest puzzles, like the mystery of dark matter. Unlike stellar black holes, which are made when big stars die and fall in on themselves, primordial black holes might have come from the early mess of the young universe, long before stars even formed. Experts think that just after the Big Bang, small but strong changes in the way matter was spread out could have made some spots crush inward and turn into black holes. So, primordial black holes did not come from dying stars. They might have popped into being because of the wild heat and pressure of the early universe. Since they were made so early, these black holes might be a lot more common than we think. Some scientists guess they are scattered all over the universe, hiding in the great emptiness of space, maybe even in our own galaxy. Because they are so small and dark, they would be nearly impossible to see directly. But the way they pull on other things with their strong gravity might still give them away. In fact, some experts think primordial black holes could help explain one of the biggest space mysteries, dark matter, the invisible stuff that makes up about 85% of all the mass in the universe. If this is true, then these ancient black holes might be the missing piece in the puzzle of how the universe works. At first glance, primordial black holes might seem like just a strange and interesting idea, something that only exists in theories. After all, no one has seen one directly, not yet at least. But scientists are working hard to find ways to prove they are real, and there are some exciting clues that suggest these mysterious objects might truly be out there. One of the most thrilling clues comes from something called gravitational waves. These are like ripples moving through the fabric of space and time, created when huge objects like black holes crash into each other. In the past few years, scientists have picked up these waves using sensitive instruments. Some of the waves they detected might have been caused by primordial black holes that could have formed in the very first moments after the universe began. If scientists keep finding these waves coming from places they didn't expect, it could be strong evidence that these ancient black holes are real and still drifting somewhere in the vast universe. Another way scientists search for signs of the early universe is by studying something called the cosmic microwave background, or CMB. This is a soft, faint glow of heat left over from the birth of the universe nearly 14 billion years ago. It's like a ghostly light that still fills space long after the Big Bang. If tiny black holes formed shortly after the universe began, they might have disturbed this ancient radiation. These disturbances could leave behind delicate patterns, almost like fingerprints, that modern telescopes and tools might be able to detect. If scientists can spot those patterns, it could be another clue pointing to the existence of primordial black holes. But the mystery gets even deeper. Primordial black holes might also help explain one of the biggest puzzles in science: dark matter. Scientists know dark matter exists because they can see its effects, like how it bends the light from faraway galaxies or how it affects the movement of stars. But no one has ever seen dark matter directly. That's because it doesn't give off light, doesn't reflect it, and doesn't absorb it. It's completely invisible. But it does have gravity, so it pulls on things we can see. If primordial black holes exist, they might actually be dark matter, or at least a big part of it. That would mean they help hold galaxies together and shape how the universe is built. What makes primordial black holes especially fascinating is that they may have formed long before stars, planets, or even light existed. While today's black holes are usually born when massive stars die and collapse, primordial black holes would have come into being when the universe was still brand new, just a hot, churning sea of energy and particles. If they really were born in that early chaos, then they would be like ancient fossils from the very first moments of time, silent witnesses to the birth of everything. By studying them, scientists hope to learn what the universe was like when it was still a baby. These black holes could carry secrets about the powerful forces that shaped all the stars, galaxies, and planets we see today. They might even tell us about the basic rules that govern how everything in the universe works, and their importance doesn't stop there. Some researchers believe that primordial black holes could help solve another deep mystery: the true nature of dark matter. Right now, dark matter is one of the most puzzling parts of the universe. Scientists believe it makes up most of the matter in the cosmos, yet it remains completely hidden from view. If primordial black holes turn out to be a part of this dark matter, it would completely change the way we understand the universe. It would open new doors in physics and help answer questions we've been asking for decades. If these ancient black holes are real, they could shake up everything we thought we knew about science. They might hold clues that help us link two of the most important scientific ideas: Einstein's theory of general relativity, which explains how gravity works on a large scale, and quantum mechanics, which describes the behavior of the tiniest particles. These two ideas don't fully agree with each other, and scientists have been searching for a way to connect them. Primordial black holes might be the key. If we could use them to bridge this gap, we might finally get closer to finding a single, powerful theory that explains everything, a theory of everything that unlocks the deepest truths about how the universe works. Right now, primordial black holes remain one of the greatest mysteries in space. Scientists have not yet found solid proof that they exist, but the hints we do have are too exciting to ignore. These black holes might be the missing piece in the puzzle of how the universe began. It's possible that they formed just moments after the Big Bang, and they might hold answers about how galaxies were born, what dark matter really is, and how unseen forces shape the cosmos. As our telescopes, satellites, and scientific tools get better, researchers are becoming more hopeful. Step by step, they are closing in on the truth, hoping to find more clues that will finally show whether these ancient black holes really exist and what role they played in building the universe we see today. The universe is unbelievably vast, and even after all our discoveries, there's still so much we don't understand. Among its many mysteries are these strange and ancient objects, primordial black holes, possibly formed in the first heartbeats after the Big Bang. They are not just fascinating, they might hold the key to one of the most important stories ever told, the story of how the universe came to be. Scientists are eager to explore this thrilling frontier, knowing that unlocking the secrets of primordial black holes could change everything we know about the cosmos. When scientists look deep into the vast stretches of space using the most powerful telescopes ever built, they're not just looking at stars and galaxies far away, they're actually peering back through time. That may sound like something out of a science fiction story, but it's a real and amazing part of how light behaves in our universe. Light doesn't move instantly, it travels at a fixed speed, about 186,000 miles every single second. That's incredibly fast, but space is unimaginably large. Because of this, the light from the farthest galaxies takes millions or even billions of years to reach us. So when we see these distant galaxies, we're not seeing them as they are today. We're seeing them as they were long ago, sometimes when the universe was still very young. As astronomers study these ancient galaxies, they've made discoveries that challenge almost everything we thought we understood about how the universe works. One of the most astonishing findings is the presence of supermassive black holes, enormous objects with gravity so powerful that nothing, not even light, can escape them. What's truly surprising is how early in the universe's history these gigantic black holes appear to have formed. They existed at a time when, according to current scientific models, they should not have even had enough time to grow. Normally, black holes are thought to begin small, formed from the collapse of huge stars that run out of fuel and explode in massive blasts called supernovae. These smaller black holes then grow slowly over millions or even billions of years by swallowing up gas, dust, and sometimes even entire stars. Over time, they can become truly massive. But in the case of these early galaxies, scientists are finding black holes that were already enormous when the universe was still in its earlier stages, less than 1 billion years old. This is a huge mystery. According to our best physics, it takes black holes billions of years to grow that big. They need time to pull in enormous amounts of matter, and that process doesn't happen overnight. Yet these ancient black holes seem to have skipped all the waiting. They were already gigantic during a time when galaxies themselves were only just starting to form. Some scientists now believe that something unusual must have happened in the early universe to allow black holes to grow much faster than they do today. Others think that perhaps these black holes didn't start as small ones at all. Instead, they may have been born in a totally different way, perhaps from giant clouds of gas collapsing directly into black holes, without forming stars first. This would be a completely different path of creation from what we've believed until now. Before we explore this mystery further, let's first understand what a supermassive black hole really is. A black hole is a region in space where gravity is so strong that nothing, not even light, which travels faster than anything else, can escape. when something passes a certain invisible boundary around a black hole, called the event horizon, it is lost forever, swallowed up by the black hole's pull. Black holes come in different sizes. Some are formed from the collapse of massive stars and are only a few times heavier than our Sun. But then there are the giants, the supermassive black holes. These cosmic monsters can be millions or even billions of times more massive than the Sun. That's like cramming an entire galaxy's worth of material into a single invisible point. These massive objects don't float aimlessly in space. In fact, they sit right at the centres of galaxies, including our own Milky Way. They act almost like the kings of their galaxies, quietly but powerfully influencing everything around them. Scientists now think that supermassive black holes may actually help shape galaxies, controlling how stars move, where new stars form, and how gas and dust are spread out. Sometimes these black holes even shoot out powerful beams of energy across the universe, changing the shape and behaviour of entire galaxies. In our Milky Way, for example, there's a supermassive black hole called Sagittarius AE sitting at the very centre. Even though we can't see it directly, we know it's there because we can watch stars swirling around it at incredible speeds, like leaves caught in a whirlpool. So despite their dark and invisible nature, black holes are anything but empty. They are powerful engines that have been shaping the universe for billions of years. Some researchers even believe that without them, galaxies might not have formed at all, or at least not in the way they have. To better understand this, let's start from the beginning. Most black holes begin their lives as smaller ones, formed when massive stars explode at the end of their life cycles. The core that's left behind collapses under its own gravity, creating what's known as a stellar mass black hole. From that point, it starts pulling in gas, dust, and anything else nearby, growing bigger over time. Over billions of years, it can become a supermassive black hole. But here's the strange part. When astronomers look at the farthest corners of space, which means looking back to the very earliest times in the universe, they found something shocking. Fully grown supermassive black holes already existed less than 1 billion years after the Big Bang. That's extremely early. To give some perspective, scientists believe the universe is about 13.8 billion years old. That means these giant black holes were already massive when the universe was still a baby. This is a huge problem for current theories. If it takes billions of years to grow a supermassive black hole, then how could one already be so big when the universe was only 700 million years old? It's like finding a fully grown tree in a garden where the seed was only planted a few days ago. Something just doesn't add up. According to our best models, black holes should have formed much later. First, huge stars would need to live out their lives, burn through their fuel, explode, and collapse. Then the black holes formed from them would need billions of years to grow, feeding on nearby matter or merging with other black holes. But some of these ancient black holes seem to have skipped all that. They were already supermassive long before there should have been enough time for that kind of growth. So what could explain this mystery? Some scientists suggest that in the early universe, black holes may have formed in a completely different way, perhaps directly from collapsing clouds of gas, without going through the star stage at all. Others think there might have been primordial black holes that formed in the first few seconds after the Big Bang itself. If these existed, they would have been around since the very beginning of time, and might help explain how some black holes grew so large so quickly. The discovery of these ancient supermassive black holes has thrown scientists into a state of wonder and confusion. It's forcing us to rethink what we thought we knew about how the universe evolved. Maybe black holes don't always follow the slow and steady path we assumed. Maybe, in the early days of the cosmos, some of them were born huge, or had a special way to grow fast. Either way, the presence of supermassive black holes in the first galaxies, just a few 100 million years after the universe began, is one of the most exciting and puzzling discoveries in modern astronomy. It's a reminder that even today, with all our advanced tools and brilliant theories, the universe still holds deep mysteries waiting to be solved. Black holes grow by pulling in things that are close to them, such as gas, clouds of dust, and even entire stars. Over time, as they gather more and more of this material, they become larger and heavier. But in the early universe, shortly after the Big Bang, there wasn't much of this material floating around yet. The first stars were only just beginning to light up the darkness, and galaxies were only in the very early stages of forming. The universe back then was still young, quiet, and mostly empty. So here's the big question that has puzzled scientists. If black holes need to feed on surrounding material in order to grow, how did some of them become so incredibly massive so quickly, at a time when there wasn't much for them to eat at all? The way we currently understand how black holes are formed and how they grow doesn't explain this. According to our best theories, it should take a very long time for a black hole to grow that big. Yet scientists have found supermassive black holes, millions or even billions of times heavier than our Sun, that already existed when the universe was only a few 100 million years old. That's just a small fraction of its current age of almost 14 billion years. This strange and surprising discovery has led scientists to believe that something unusual must have happened in those early days. Either black holes found a way to grow much faster than we ever thought was possible, or there's something big, something important, we still don't understand about how the universe worked back then. To try to explain this mystery, scientists have come up with several fascinating ideas. One idea is that some black holes may have skipped the usual growth process entirely. Normally, black holes form when very large stars run out of fuel and collapse under their own weight. But in the early universe, there might have been huge clouds of gas, far bigger than anything we see today, that collapsed directly into black holes without first becoming stars. If this happened, then these black holes would have started out as giants, already much bigger than normal ones. That would have given them a big head start in their race to grow even larger. Another idea is that black holes in the early universe might have been able to grow much faster than they do today. Usually there's a limit to how quickly a black hole can grow. As it pulls in more matter, it starts to shine very brightly due to the energy released by that infalling material. This light creates pressure, and that pressure pushes back against more material trying to fall in. This balance is called the Eddington limit, and it puts a cap on how fast black holes are allowed to grow, at least under normal conditions. But some scientists think that, in very special situations, black holes in the early universe might have broken that rule. They might have been able to grow so quickly that they push past the Eddington limit, growing at a rate we once thought was impossible. If true, this could explain how they became so big in such a short amount of time. There's also another curious theory that goes back to the very beginning of time itself. Some researchers believe that special kinds of black holes, called primordial black holes, may have formed just moments after the Big Bang, when the universe was still a hot, dense and chaotic place. These black holes could have formed not from stars but directly from extreme fluctuations in the early universe. If they were born already big, then they would have had a huge advantage and could have grown into supermassive black holes much faster than others. It would be like entering a marathon with a huge lead over everyone else. Yet another idea is that black holes might not have grown alone. Instead, in the early universe, many small black holes could have formed in groups or clusters. Over time, these black holes may have been pulled toward each other by gravity and eventually collided and merged. These rapid collisions could have created bigger and bigger black holes in a very short amount of time, perhaps fast enough to produce supermassive black holes just a few 100 million years after the Big Bang. But maybe the most mysterious idea of all is that these early giants are trying to tell us something even deeper, that we may be missing something fundamental about how the universe works. Some scientists think that understanding these ancient supermassive black holes might lead to revolutionary new ideas in physics. We might discover unknown forces, new types of matter, or strange processes that helped black holes grow faster than we ever believed possible. If any of these things are true, it could completely change our understanding of the cosmos. That's why astronomers are so excited about the tools they now have to explore the farthest corners of space. One of the most powerful tools is the James Webb Space Telescope, often called JWST. It was launched in the year 2021, and it's now peering deep into space and far back in time, capturing breathtaking images of some of the oldest galaxies ever seen. By carefully studying these ancient galaxies and the black holes that lie at their centres, scientists hope to uncover how such enormous cosmic objects came to exist so soon after the universe was born. Every new photo taken by JWST is like a window into the distant past, and with each new discovery, we move one step closer to solving one of the universe's biggest mysteries. How did supermassive black holes come into being so quickly? Right now, the discovery of these ancient cosmic giants has scientists both amazed and puzzled. According to everything we thought we knew, they shouldn't even exist yet, but they do. Their presence shakes the foundations of our current understanding of how black holes form and grow. The discovery of the very first stars ever born in the universe takes us on a thrilling journey deep into the distant past, so far back that it's almost like peering into the universe's baby photos. These first stars, known as population 3 stars, are incredibly rare and mysterious. What makes them so special is that they were made entirely from just 2 basic ingredients: hydrogen and helium, the lightest and simplest elements in the universe. They were formed not long after the universe itself came into existence, during a time when everything was still new, chaotic and brimming with energy. With the incredible power of the James Webb Space Telescope, we now have the ability to look further back in time than ever before. This telescope is like a cosmic time machine, helping scientists study these ancient stars and explore moments that happened more than 13 billion years ago. It gives us a rare window into the universe's earliest days, long before Earth, the Sun, or even the Milky Way galaxy existed. The story of these ancient stars begins with the greatest event in all of cosmic history, the Big Bang, which happened around 13.8 billion years ago. This wasn't just a big explosion. It was the birth of time, space, and everything that would ever exist. In the very first few minutes after the Big Bang, the universe was unimaginably hot and dense. It was a swirling soup of energy and particles so intense that only the simplest elements could take shape. These were hydrogen, helium, and just a tiny trace of lithium. Hydrogen came first. It's the most basic of all the elements. Each atom is made of just 1 proton. Helium followed close behind, with a slightly more complex structure of 2 protons and 2 neutrons. These 2 elements became the raw material for everything that would follow: stars, planets, galaxies, and even life. But in those early days, heavier elements like carbon, oxygen, or iron didn't exist at all. Those would only be created later, deep inside stars, like secret recipes cooked in the fiery cores of these cosmic giants. During this time, the universe was a vast, cold, and silent place. It was completely dark. There were no stars, no galaxies, and no light. Just invisible clouds of hydrogen and helium drifting through the void. This quiet time in the universe's history is called the Cosmic Dark Ages. It lasted for hundreds of millions of years, a time when the universe was in waiting, preparing for its first burst of light. But even in the darkness, something was slowly happening. Gravity, the invisible force that pulls things together, began its patient work. It started to tug on the scattered clouds of hydrogen and helium, slowly pulling them into tighter and denser clumps. As these clouds collapsed under their own weight, they grew hotter and hotter. Then, something incredible happened. The first stars were born, igniting for the first time and ending the long, cosmic night. These very first stars were unlike anything we see today. They were enormous, blazing hot, and made only of hydrogen and helium. No other elements had been created yet. Scientists gave them the name population 3 stars to set them apart from the stars that came later, which contain heavier elements formed by earlier generations of stars. Population 3 stars didn't just shine, they transformed the universe. Their light kicked off one of the most important moments in cosmic history, called cosmic reionization. Before these stars lit up, the universe was filled with thick clouds of neutral hydrogen gas that blocked light from travelling freely. But when the first stars began to burn, they gave off powerful ultraviolet radiation. This radiation had enough energy to strip electrons from the atoms of hydrogen, turning the gas into an ionized state. In simpler terms, it made the gas transparent, allowing light to finally move across the universe. This changed the entire appearance of the cosmos, turning it from a foggy, invisible space into one filled with starlight. These stars weren't just big, they were gigantic. Many of them were hundreds or even thousands of times larger than our Sun. Because of their massive size, they burned through their fuel incredibly fast. While a star like our Sun can last for billions of years, these giants lived for only a few million years, a short flash on the cosmic timeline. But their deaths were anything but quiet. When these stars ran out of fuel, they exploded in spectacular fashion, supernovae so powerful that they lit up entire regions of the sky. During these explosions, the first heavy elements like iron, gold, and carbon were released into space. These elements were essential. They became the seeds that formed new stars, planets, and eventually life. In this way, the death of a population 3 star wasn't really an ending. It was a new beginning, a creative explosion that helped shape everything that came after, including us. Studying these stars is one of the most difficult challenges in modern astronomy. Because they were so far away and lived so long ago, their light has taken billions of years to reach Earth. That light has stretched and faded over time, making it incredibly faint. Scientists often can't see these stars directly. Instead, they search for clues left behind, such as how these stars affected the gas around them. One important clue is the formation of giant ionized bubbles, huge regions of space where the radiation from population 3 stars stripped electrons from hydrogen gas. By examining the size and shape of these bubbles, astronomers can learn a lot about the first stars that created them, including how powerful they were and how quickly they lit up the early universe. But the study of these stars is about more than just looking backward. It also helps us understand how life began. Without population 3 stars, the heavy elements that make up planets, air, water, and living things would never have existed. By learning more about them, we get closer to answering some of the biggest questions of all. Where did we come from? And how did life first begin in the universe? These stars also help scientists understand the formation of galaxies, black holes, and other massive structures in space. By studying how population 3 stars were born, how they lived, and how they died, scientists can piece together the story of the universe, from the first sparks of light to the complex web of stars and galaxies we see today. Every new discovery brings us closer to understanding how the universe evolved over the past 13.8 billion years. Thanks to the James Webb Space Telescope, we are entering a new golden age of discovery. This telescope is already helping scientists learn more about how the first galaxies and stars came into being. And in the near future, even more powerful telescopes will take the search further, allowing us to collect more data and, possibly, even find leftover traces of the very first stars themselves. If that happens, it would be like opening a time capsule sealed at the beginning of the universe, offering a direct connection to the ancient past. The study of population 3 stars isn't just one of the most exciting areas of astronomy, it's a journey to the origins of everything. These first stars were the creators of the ingredients that make up all we see and are today. Heavy elements are made through a process called nucleosynthesis, where the centers of atoms join together in the cores of stars. The heaviest elements are made during a special process known as the fast neutron capture process, or R process, which happens when neutron stars crash into each other or explode in strong star explosions. Nucleosynthesis itself is the making of new atomic centers from protons and neutrons, the basic parts of matter, that already exist. According to scientists, the very first atomic centers formed just a few minutes after the Big Bang through a process called Big Bang nucleosynthesis. About 20 minutes after the Big Bang, the universe had grown and cooled enough that high-energy crashes between particles slowed down. Because of this, only the simplest reactions happened, leaving behind mostly hydrogen and helium, with small amounts of other elements like lithium and deuterium, a type of hydrogen. Over time, stars and their explosions created the wide variety of elements we see in the universe today, a process called cosmic chemical change. However, the universe still has mostly hydrogen and helium, with heavier elements, called metals by space scientists, making up only a small part of the total mass. Stars are like giant factories where lighter elements join into heavier ones in their centers, giving off energy while doing so. This is known as star nucleosynthesis. The joining reactions create lighter elements, including iron and nickel in the biggest stars. The products of these joining reactions mostly stay inside the stars unless they are pushed out by star winds or explosions. Neutron capture reactions like the R process and S process help make even heavier elements, starting with iron and going up. When a star explodes in a supernova, it makes even more elements, especially those between oxygen and rubidium. This happens because of the release of elements formed in earlier star processes, the strong joining reactions in the blast, and the R process that takes place when neutrons are quickly added during the explosion. A more recent finding is that neutron star smash-ups, when two neutron stars hit each other, also make a large amount of heavy elements through the R process. The crash lets out a huge amount of matter filled with neutrons, which quickly turns into new, heavier elements. Another way elements are made is called cosmic ray spallation. This happens when high-energy space rays hit atomic centers and break them apart. This process is important for making lighter elements, like helium-3, beryllium-9, and boron types, which are not made by star nucleosynthesis. Cosmic ray spallation can happen in space, on space rocks, or even here on Earth in the air or ground, adding to the spaceborne elements found on our planet. On Earth, new atomic centers also form through radiogenesis, which happens when old radioactive elements like uranium, thorium, and potassium-40 slowly break down over time. Looking back to the Big Bang, scientists believe that the first building blocks of matter, protons and neutrons, formed from a super-hot soup of particles about 13 billion and 800 million years ago, as the universe cooled down. In just a few minutes, these particles came together to form the first atomic centers, including lithium and beryllium. But elements like carbon couldn't form yet because the conditions weren't right, and the joining process mostly stopped after about 20 minutes as the universe got bigger and cooler. This event, called Big Bang nucleosynthesis, made the first early elements. Stars that formed early in the universe used these light elements, hydrogen, helium, lithium, beryllium, and boron, to build heavier ones. These light elements were left over from the Big Bang and cosmic ray spallation. Over millions of years, space rays, mostly high-energy protons, caused heavier elements in space gas and dust to break apart, creating new light elements like helium-3, lithium, beryllium, and boron. Carbon, which wasn't made during the Big Bang, was made later in big stars through a process called the triple alpha process, marking a big step in the story of how elements were formed. The process of making heavier elements needs very high heat and pressure, conditions found in stars and star explosions. This process started when hydrogen and helium, made by the Big Bang, gathered together to form the first stars about 500 million years later. Since that time, stars have kept forming in galaxies. The first chemical elements, known as early atomic types, were made by processes like Big Bang nucleosynthesis, star nucleosynthesis, supernova nucleosynthesis, and rare events like neutron star crashes. Some elements, like argon-40, were made later through the slow breakdown of radioactive elements. Over time, the mixing and changes on Earth changed these original elements into what we now call Earth's natural mix. The heavier elements, which came after the Big Bang, range from carbon to plutonium. These elements were made through nuclear reactions that involved the strong and weak forces between atomic centers, a process called nuclear joining, which includes both fast and slow neutron capture, along with nuclear breaking and radioactive breaking like beta decay. The stability of different atomic centers, based on how many neutrons and protons they have, greatly affects how these reactions happen. That's why the study of how elements are made in space is so important for scientists who study stars and atomic behavior, also known as nuclear space science. At first, scientists thought all the chemical elements were made at the beginning of the universe, but there was no clear physical reason for it. Over time, it became clear that hydrogen and helium were much more common than other elements. In fact, they make up almost everything in the universe, while all other elements together make up less than 2% of the mass in our solar system and others. Oxygen and carbon were found to be the next most common, and it was clear that lighter elements, especially those made of whole numbers of helium-4 centers, called alpha types, were much more common. In the year 1920, Arthur Stanley Eddington first said that stars make their energy by joining hydrogen into helium, and guessed that heavier elements might also form in stars. But this idea wasn't widely accepted because the nuclear reactions involved weren't fully understood. It wasn't until just before World War II that Hans Bethe explained how hydrogen joins into helium through nuclear reactions. After the war, Fred Hoyle made big steps in showing how heavier elements form in stars, explaining how all the elements heavier than hydrogen were made from it. Hoyle said that hydrogen is always being made in the universe from empty space and energy, without needing a starting point. His work also explained how the number of elements grows over time as the galaxy gets older. This idea was expanded in the 1960s by scientists like William A. Fowler, Alistair G.W. Cameron, and Donald D. Clayton. A famous paper in the year 1959 by E.M. Burbidge G.R. Burbidge, Fowler and Hoyle summed up the progress in the field, showing new ways that heavy elements change inside stars, ways that astronomers could study. The idea of the Big Bang itself was suggested in the year 1931 by Georges Lemaitre, a Belgian scientist, who said that the growing universe must have started from a single point, a first atom. He guessed that if we followed the universe's growth backward, it would shrink to this point before time and space existed. Hoyle, in a 1949 BBC radio show, came up with the name Big Bang, although he said it wasn't meant as an insult. He just used it as a lively picture to compare the Big Bang idea with others. Lemaitre's idea was important in explaining the high amount of helium and the presence of deuterium and other elements between helium and carbon, which were found not just in stars but also in space between stars. In the end, both Lemaitre's and Hoyle's ideas about how elements are made were very important for helping us understand the makeup of the universe. The theory of nucleosynthesis tries to explain why different chemical elements and their types are found in different amounts, all by looking at natural processes. A big reason this theory was created comes from the strange shapes seen when the number of elements is graphed against their atomic number. When these amounts are shown on a chart, the line looks jagged and sharp, with some elements much more common than others, by as much as 10 million times. One of the most important discoveries in this research was a table of element amounts made by scientists Hans Suess and Harold Urey. They based their table on the unchanged amounts of elements found in space rocks that hadn't changed much. This table, shown on a special scale that grows in steps, helps smooth out the sharp jumps in element amounts because the scale can handle the large differences in values on the up and down axis. Different space-related processes are believed to cause nucleosynthesis, with most of them happening inside stars. The chain of nuclear joining reactions in stars, called hydrogen burning, can happen in two main ways: the proton-proton chain or the CNO cycle. There are also later burning stages: helium burning, carbon burning, neon burning, oxygen burning, and silicon burning. These joining reactions help make elements up to iron and nickel. This is the point where nucleosynthesis creates the most stable elements per atomic part. For heavier elements, other processes are involved. In stars, a neutron capture process called the S process can make them, but in more extreme events, like star explosions or when neutron stars crash, other processes happen. These include the R process, where neutrons are quickly added, the ART process, and the P process, also called the gamma process, where high-energy light breaks up existing atomic centers. Star nucleosynthesis is the process that makes new atomic centers inside stars. This happens during a star's life and is key to understanding how elements, from carbon to iron, are spread through the galaxy. Stars are huge nuclear ovens where lighter elements like hydrogen and helium join together to make heavier ones as the star changes. As the star's center gets hotter and denser, it makes heavier elements. One of the most important of these is carbon, which is made through a group of reactions called the triple alpha process. Carbon is very important because making it starts the creation of even heavier elements. In fact, carbon helps release free neutrons inside stars, starting the S process. This process slowly turns iron into even heavier elements like gold and uranium. When elements are formed inside stars, they don't stay trapped there forever. As stars grow older, they begin to lose some of their mass. During the final parts of their lives, stars blow out these newly made elements into space. This happens through something called stellar winds, powerful streams of particles that flow out from the surface of the star. In smaller stars, this takes place during a phase called the planetary nebula stage. In much bigger stars, this dramatic release happens when the star reaches the end of its life and explodes in an enormous event called a supernova. These kinds of explosions are some of the main ways that heavy elements are scattered across the universe. The first strong proof that stars are the factories where elements are created came when scientists noticed that the gas floating between stars, gas that helps form new stars, was becoming richer in heavy elements as time went on. This meant that stars born later in the galaxy's history had more heavy elements in them than stars that were born much earlier. Then, in the year 1952, scientists made a very important discovery. They found the element technetium in the atmosphere of a red giant star. Technetium is a radioactive element that breaks down quickly, which means it couldn't have been floating around for long. It had to have been made recently inside that star. This gave scientists direct evidence that nuclear reactions were happening in stars. More support for this idea came when astronomers discovered a lot of the element barium in certain stars, especially stars in a late stage of life known as the asymptotic giant branch. These older stars had much more barium than younger stars, which pointed to a slower process called the S process happening inside them, another way that stars build heavy elements over time. Today, we have even more amazing clues from something called stardust, tiny solid grains that formed in the atmospheres of stars and later became part of meteorites that fell to Earth. These grains are known as pre-solar grains because they were created before our sun was even born. By looking closely at the chemical makeup of these grains, scientists can figure out what was going on inside the stars that produced them. Each grain carries a special mix of isotopes, different forms of elements, that tells the story of the nuclear reactions that took place inside those stars as they reached the ends of their lives. Another key process, called supernova nucleosynthesis, takes place in the extremely hot and violent environment of a supernova explosion. During this process, elements from silicon to nickel are created through fast-moving fusion reactions. These reactions fuse atomic nuclei with silicon-28, forming a kind of temporary balance called quasi-equilibrium. In this state, the material isn't completely stable, but there's a huge amount of silicon-28 in the mix. This idea was a major leap forward in helping scientists understand how medium-weight elements, those between silicon, which has atomic number 14, and nickel, which has atomic number 28, are made. It replaced an earlier incorrect theory from a paper known as B²FH, which had confused scientists and overshadowed important earlier research by Fred Hoyle in the year 1954. But the story doesn't end with quasi-equilibrium. There's also a much faster process called the R process, or rapid neutron capture process. In this process, atomic nuclei quickly grab onto lots of neutrons, creating elements even heavier than nickel. This is a major way that very heavy elements like uranium and thorium are made. The R process was first described by scientists named Seeger, Fowler, and Clayton. What's truly surprising is that the R process can happen even in stars made almost entirely of hydrogen and helium, something that was once thought to be impossible. This process plays a huge role in creating many of the heaviest elements in the universe. One of the clearest signs of the R process comes from very old stars that formed in galaxies with very low levels of metals. These ancient stars still contain R process elements, showing that this powerful reaction must have happened inside stars, no matter how poor in heavy elements the galaxy was. There's also another process called the RP process, or rapid proton capture process. It's similar to the R process, but instead of just capturing neutrons, atomic nuclei also grab protons. Scientists are still studying this process to understand how important it is in the creation of different elements, but it may play a role in making certain rare ones. During the powerful blast of a supernova, atomic nuclei with equal numbers of protons and neutrons are formed in large numbers. This balance makes the nuclei more stable. For example, when oxygen and silicon fuse during the supernova, they produce atoms that have an equal number of protons and neutrons, like calcium-40. These are stable isotopes. But if the resulting atoms are heavier, even with equal protons and neutrons, they tend to be unstable and break apart after the explosion. When this happens, they decay into more stable forms, such as iron-56, chromium-52, and titanium-48. This decay process also releases powerful gamma rays. Scientists can detect these gamma rays and use them to figure out what elements were created during the supernova. The detection of these gamma ray signals was a huge moment for gamma ray astronomy and gave solid evidence for explosive nucleosynthesis. One of the most exciting discoveries came from the supernova that exploded in the year 1987. Scientists were able to detect gamma ray lines coming from the explosion. These lines matched radioactive elements like cobalt-56 and cobalt-57. That meant the supernova had actually created those elements during the blast. This was strong proof that explosive nucleosynthesis really happens in stars, and it marked a big step forward in a field called nuclear astronomy. The information gathered from those gamma rays was so important that it helped shape the plans for NASA's Compton Gamma Ray Observatory. We also know that supernovae create heavy elements thanks to more stardust. As the supernova explodes and then begins to cool, solid grains start to form. These grains, part of what we call cosmic dust, carry the fingerprints of the explosion that made them. Some of them contain unusual isotopes like titanium-44. This particular isotope has been found in the stardust grains that formed during the explosion. The discovery of titanium-44 in these grains confirmed earlier ideas that supernovae help create cosmic dust. It also gave scientists new details about how explosive nucleosynthesis works. Even today, by studying the strange mix of isotopes inside stardust grains, scientists continue to unlock the secrets of how the elements in our universe were born from the deaths of stars. For thousands of years, people have looked up at the night sky with wonder in their eyes and questions in their hearts. They've asked one of the oldest and most powerful questions we know: are we alone in the universe? As humans stared at the stars above, they imagined other worlds, maybe like Earth, maybe completely different, where life might exist. The night sky, with its sparkling light scattered across endless darkness, has always been full of mystery. It stirred the minds of scientists, poets, explorers, and dreamers alike. With billions upon billions of stars shining in the vast stretches of space, many believe that some of these stars must have planets orbiting around them, planets that could perhaps be warm, wet, and alive. But for most of human history, this was only a dream, a guess, a hope with no proof. No one had actually seen a planet outside our solar system. That all began to change in the late 20th century. Thanks to amazing advances in technology, like space telescopes far more powerful than anything before, and daring space missions, astronomers started to uncover something incredible. They discovered that Earth is not alone. In the past few decades, scientists have confirmed the existence of thousands of planets beyond our solar system. These distant worlds are called exoplanets, and they orbit stars far away from our Sun. This discovery completely changed how we see the universe and our place within it. It made the universe feel both bigger and more exciting than ever before. Out of the many thousands of exoplanets found so far, only a small handful seem to have the right kind of environment for life as we know it, things like the right temperature, liquid water, and a stable atmosphere. But the search isn't over. In fact, it's just beginning. With every new discovery, we move a little closer to answering that deep ancient question: is life out there somewhere among the stars? Now, let's dive deeper into what exoplanets are. Exoplanets are planets that orbit stars other than our Sun. Some are small and rocky like Earth, others are enormous balls of gas, more like Jupiter. And then there are some so strange, so unlike anything we know, that they seem to belong in science fiction. Astronomers have found exoplanets in places we never thought planets could exist. Some are icy and cold, stuck in an eternal winter. Others are blazing hot, with molten lava oceans covering their surface. And in the most extreme cases, scientists have even found planets where it rains iron. The heat in their atmosphere is so intense that metal turns into vapor and then condenses into droplets, falling from the sky like fiery rain. The very first exoplanets were discovered in the year 1992, and they were found in a truly unexpected place, circling a pulsar, which is a type of dead star that shoots out beams of radiation. These planets didn't look anything like the ones in our solar system, but they proved something huge. Planets can form almost anywhere. Then, in 1995, scientists found 51 Pegasi b, the very first exoplanet orbiting a Sun-like star. It was a giant gas planet, and its discovery opened the door to an entirely new era in astronomy. Since then, astronomers have found more than 5,005 exoplanets, and new ones are being added all the time. Using advanced instruments like the James Webb Space Telescope, scientists are not only spotting these distant worlds but also studying their atmospheres, looking for gases or signs that could hint at life. But not all exoplanets are the same. They come in many types and sizes, and scientists group them into categories based on what they're made of, how big they are, and how close or far they are from their stars. One major group of exoplanets is called gas giants. These are huge planets made mostly of hydrogen and helium, two of the lightest gases in the universe. Jupiter and Saturn, two of the most famous planets in our solar system, are examples of gas giants. They're so big that over 1,300 Earths could fit inside Jupiter alone. Unlike Earth, gas giants don't have a solid surface. If you tried to land on one, you'd fall through thick clouds of gas that get hotter and more pressurized the deeper you go. In fact, deep inside a gas giant, hydrogen gas gets squeezed so tightly that it turns into a liquid. Scientists believe there might be a solid core hidden way down at the center, but it's impossible to confirm because no spacecraft can survive the journey. Gas giants are often the first planets we find when looking at new star systems. That's because they're so massive, they block more light when passing in front of their star, a method called a transit. These transits help scientists detect the planet even though it's light years away. Some of the gas giants found outside our solar system are even stranger than Jupiter or Saturn. Some orbit very close to their stars and are called hot Jupiters. They're so hot that their atmospheres boil. Others are known as ice giants, like Neptune and Uranus, and are filled with substances like water, ammonia, and methane. Gas giants might seem too wild or too extreme to support life, but studying them still helps us learn how planets form and evolve. They even raise the question, could moons around gas giants hold life, like in the case of Jupiter's icy moon Europa? Another type of fascinating planet is the Neptune-like planet, sometimes called a mini-Neptune. These are similar to Uranus and Neptune, which orbit far from the Sun in our own solar system. Like their bigger cousins, mini-Neptunes are mostly made of gas and don't have solid surfaces. Uranus and Neptune are well known for their chilly blue appearance, which comes from methane in their atmospheres. Their weather is wild, strong winds, powerful storms, and layers of clouds. They also contain icy materials like water, ammonia, and methane, which is why they're called ice giants. Mini-Neptunes are smaller than gas giants like Jupiter, but still bigger than Earth. Their atmospheres are thick but not as deep or heavy. Some may have a rocky or icy core at the centre, but since they're far away we can't see this directly. What makes these planets so exciting is how common they are. In fact, many of the exoplanets discovered so far fall into this category. Mini-Neptunes might actually be one of the most common types of planets in the entire galaxy. Each of these planets is unique. Some have heavy, cloud-filled skies that trap heat and create steamy environments. Others may have lighter, more mixed atmospheres with interesting weather patterns. While they don't have surfaces to walk on, they could have strange and beautiful landscapes hidden beneath their clouds, or even oceans deep below their gas layers. Even though mini-Neptunes don't have powerful magnetic fields or massive storm systems like their larger cousins, they can still be very active worlds. Scientists are eager to learn more about them, and new discoveries might tell us whether any of them could have the right conditions for life. Then come super-Earths, which are amazing planets that are bigger than Earth but smaller than Neptune. They are much larger than our home planet, but they don't grow to the huge size of gas giants like Neptune or Jupiter. The name super-Earth only talks about how big and heavy they are, not what they are made of or whether they can support life. Some of these planets might have hard, rocky surfaces like Earth, while others might be covered in thick layers of gas or ice. One of the most exciting things about super-Earths is that some of them might have the right conditions for life. Scientists think that if a super-Earth goes around its star at the right distance, where it's not too hot and not too cold, there could be liquid water on its surface. Since water is needed for life as we know it, these planets might be able to support living things, from tiny germs to more complex creatures. Another interesting thing about super-Earths is that they have strong gravity. Because they are heavier than Earth, their pull would be stronger. This means that if people landed on one of them, they might feel much heavier and have a harder time walking or moving. However, having a thick atmosphere could also help block dangerous space radiation, which might make some of these planets even better for life. Super-Earths come in many kinds. Some might be covered in wide oceans that spread across the whole planet. Others might have thick clouds and a heavy atmosphere that holds in heat, making them more like Venus. Some might even be full of useful materials or have strange chemicals that we have never seen before. Because they are bigger than Earth, these planets might also have hotter, more active centers. This could lead to more volcanoes. Volcanic eruptions over millions of years can help build a steady atmosphere by releasing gases. If a super-Earth has a magnetic field, like Earth does, it could also protect the planet from dangerous solar winds, making it even more like Earth. Astronomers have already found many super-Earths in faraway star systems, and new telescopes are helping scientists look at them more closely. Some of the best-known ones, like Kepler-22b and TOI 700d, have gotten people excited because they seem to be in the habitable zone of their stars. where conditions might be good for life. Terrestrial planets are the rocky planets in our solar system that include Earth, Mars, Venus, and Mercury. These planets are special because they are mostly made of solid rock and metal, giving them a hard surface. This is very different from gas giants like Jupiter and Saturn, which are mostly made of gas and don't have a solid surface to stand on. The solid makeup of terrestrial planets makes them especially interesting to scientists looking for places where life might exist. Earth is the most well-known of these rocky planets because it is the only one we know that has life. Scientists are always searching for other planets that are like Earth, hoping to find another place in the universe where life might live. This is why planets like Mars, Venus, and Mercury are so interesting to space experts. Mars, for example, is a big focus for scientists because it has a rocky surface with signs of old rivers and lakes. Some experts think Mars might have had the right conditions for life long ago, and they want to know more about its past. NASA has sent many robots to Mars to explore its surface and collect clues that could tell us if life ever lived there. Venus is another rocky planet that gets a lot of attention, but for a different reason. It is often called Earth's twin because it is about the same size and shape. But Venus is extremely hot and covered in thick clouds of poisonous gas, making it a very harsh place for life as we know it. Even so, scientists are still curious about Venus because learning about its wild weather and hot surface could help us understand how planets change and why Venus ended up so different from Earth. Mercury, the smallest rocky planet, is also very interesting to study. It is closest to the Sun, so it goes through extreme changes in temperature, burning hot during the day and freezing cold at night. Scientists want to know how Mercury formed and how its surface has changed over billions of years. Since it has almost no atmosphere, it's a good place to study how space rocks crash into a planet's surface. One thing these rocky planets all have in common is their solid surfaces, which makes them stand out in our solar system. Scientists are also looking for other rocky planets outside our solar system in a place called the habitable zone. This is the area around a star where the conditions might be just right for liquid water to exist, which is key for life. Rocky planets are not just interesting because of their solid surfaces, but also because they may hold clues about whether life can grow on other worlds. Scientists keep studying Earth's neighbours and far-off planets, hoping to uncover the secrets of these amazing worlds. Not every planet can support life. For a planet to be able to have life, it needs just the right conditions to allow liquid water to stay on its surface. But why is water so important? Well, every living thing we know, whether it's tiny bacteria, tall plants, or animals like us, needs water to live. Scientists believe that if a planet has water in liquid form, it has a much better chance of being able to support life. There are a few key things scientists look at when trying to figure out if a planet outside our solar system might be able to support life. The habitable zone, often called the Goldilocks zone, is a special area around a star where a planet is just the right distance to be not too hot and not too cold. Think of it like the perfect spot where liquid water can exist and life has a chance to grow. This zone is very important because water is needed for life. If a planet is too close to its star, like Venus, it becomes way too hot. The heat is so strong that any water would quickly boil and disappear into the air, leaving the planet dry and lifeless. It's like being too close to a campfire. Everything would burn. On the other hand, if a planet is too far away from its star, like Mars, it gets too cold. The cold is so intense that any water would turn into ice, making it impossible for liquid water to stay on the surface. It would be like being so far from the sun that everything is frozen, no chance for life. But Earth sits in just the right place, in the middle of the habitable zone. It is not too close and not too far from the sun. This perfect distance allows Earth to have water in liquid form, forming rivers, lakes, oceans, and clouds. These water sources are key to all life on Earth, giving animals and plants a place to live and the water they need to grow. Because of this, Earth is a rare planet full of life, where water flows and the temperature is just right. In simple terms, the habitable zone is like the Goldilocks story. Everything is just right. It's a place where water can flow, temperatures stay safe, and life can grow. Without this special zone, Earth would be either burning hot or frozen solid, both too extreme for life. Earth's perfect spot in this zone is one big reason why it is so special, and unlike any other planet we know. A planet's atmosphere is like a warm, protective blanket, that covers it and keeps it safe. You can think of it as a shield that protects the planet from space. This blanket holds in heat from the sun, helping to keep the planet's temperature from getting too cold or too hot. Without this shield, a planet could go from freezing at night to boiling during the day, making it too hard for life to survive. On Earth, our atmosphere is made up of many important gases, and one of the most important is oxygen. It's the gas we breathe to stay alive. But oxygen isn't the only gas that matters. There's also carbon dioxide, which helps keep Earth warm. It traps heat in the air, a process called the greenhouse effect. Without enough carbon dioxide, our planet would be too cold. But too much of it could make the planet too hot. So the balance has to be just right. Now think about the Moon. Unlike Earth, the Moon has no atmosphere at all. This means it has nothing to protect it from the dangers of space. In the daytime, it can get hotter than 250 degrees Fahrenheit, and at night it can drop to below minus 280 degrees Fahrenheit. Without an atmosphere to hold in the heat, or block harmful rays from the sun, life can't survive there. On the other hand, Venus has a super thick atmosphere made mostly of poisonous gases like carbon dioxide. This causes a runaway greenhouse effect, trapping heat so strongly that the surface temperature on Venus reaches around 900 degrees Fahrenheit, hotter than an oven on high. Because of this heat and the toxic air, life cannot survive on Venus. For a planet to support life, it needs the right kind of atmosphere. The gases must be balanced to keep the surface warm enough but not too hot, and also protect it from space radiation. If there is too little atmosphere, the planet freezes. If there is too much, it burns. Earth has the perfect mix, which is why life is able to grow here. Earth is special in many ways, but one of its most important features is its magnetic field. This magnetic field acts like a huge shield, protecting us from dangerous energy from the sun. The sun is always sending out strong waves of energy called solar radiation. Without Earth's magnetic field, these waves would hit the planet directly and could slowly take away the atmosphere. Now, let's think about what happened to Mars. Unlike Earth, Mars lost its magnetic field a long time ago. This means that there is no shield to protect it from solar radiation. Over millions of years, the sun's rays slowly began to strip away the Martian atmosphere. Today, Mars has a very thin atmosphere, which isn't able to keep in heat or protect the surface. As a result, the surface of Mars is dry, cold, and barren. There are no oceans, no forests, and no life. Scientists believe that Mars might have once had a thicker atmosphere, and it may have been more Earth-like, with flowing water and perhaps even some form of life. But without a magnetic field to protect it, the sun's radiation took its toll, leaving Mars the cold and desolate planet we see today. So, the magnetic field on Earth isn't just a random feature, it's a life-saving shield. It's one of the reasons Earth is so special in the vastness of space. Without it, our planet might have faced the same fate as Mars, becoming a lifeless, inhospitable place where survival would be impossible. Even though a planet is located in the habitable zone, which means it's at just the right distance from its star to possibly support life, there's still something essential it needs: liquid water. You see, water is the foundation for life as we know it, and while frozen water might exist on some exoplanets, planets that orbit stars outside our solar system, it isn't enough on its own. For life to thrive, water must be in liquid form. This is because liquid water is the perfect environment for chemical reactions, which are necessary for life to develop and continue. Think about Earth. Without oceans, lakes, or rivers, life would have a much harder time surviving. So when scientists study exoplanets, they focus on finding clues that could indicate the presence of liquid water. This could be in the form of large bodies of water like oceans, or perhaps rivers and lakes. In some cases, there might even be underground water, hidden beneath the surface, that could support life in a completely different way. The search for these signs isn't simple, though. Scientists use powerful telescopes and complex technology to detect exoplanets and analyze their atmospheres, looking for hints that water might exist. They search for the right temperatures and conditions that would allow water to remain liquid, not frozen or vaporized. It's a delicate balance because a planet too close to its star could have water vaporized into gas, while one too far might have it frozen solid. These efforts to find liquid water on other planets are critical because they give scientists the best chance of finding life beyond Earth. not every star is capable of supporting planets where life could exist. Stars come in all sizes, and their size plays a crucial role in determining whether or not they can have habitable planets orbiting them. Some stars are very big, much larger than our own Sun. These giant stars burn incredibly hot and fast, using up their fuel much quicker than smaller stars. They shine brightly for a short period of time, but this rapid burning process means that any planet orbiting them would only have a limited window of time before the star exhausts its fuel and dies. This short lifespan is not ideal for life to develop and thrive. On the other hand, there are smaller, cooler stars. These stars burn much slower and live for a very long time, but because they are not as hot, they may not provide enough warmth for planets that orbit them. A planet too far away from one of these stars might not receive enough energy to maintain liquid water, which is considered one of the key ingredients for life as we know it. Without the right amount of warmth, these planets would likely be too cold to support life. The stars that seem to be the best candidates for hosting habitable planets are the ones that are similar in size to our Sun. These Sun-like stars have just the right balance of heat and stability. They shine steadily for billions of years, providing a consistent source of energy for any planets orbiting them. This stability gives life the time it needs to develop and evolve. However, even stars that are a little smaller than our Sun, known as K-dwarfs, are also good candidates for hosting habitable planets. While these stars are slightly cooler, they still have a stable output of energy and a very long lifespan, making them ideal for sustaining life over extended periods. These stars burn their fuel at a slower rate, allowing them to shine for tens of billions of years, much longer than our Sun will. In short, for a planet to have the right conditions for life, the star it orbits must provide a stable and consistent source of energy. Stars that are too big burn out too quickly, while those that are too small may not offer enough warmth. The best candidates are stars like our Sun, or slightly smaller K-dwarfs, which strike the perfect balance between heat, stability, and longevity. Exoplanets are incredibly far from Earth, so scientists can't actually see most of them with their eyes. Instead, they use clever methods to figure out that these distant planets are out there. By studying how light behaves or observing how the stars move, they can uncover the hidden secrets of these faraway worlds. These techniques allow scientists to detect planets that we may never be able to see directly, giving us a glimpse into the vastness of space. The transit method is one of the most widely used ways that scientists detect planets beyond our solar system, called exoplanets. It's like watching a tiny shadow pass across a bright light. Here's how it works. Scientists begin by closely observing a star, which is far away in space. This star is often hundreds or even thousands of light years away from Earth. Now, stars shine very brightly, so when a planet moves in front of one, it causes a slight but noticeable change in the star's brightness. Imagine the planet as a small, moving object that briefly blocks out a little bit of the star's light as it crosses in front of it. This dimming of the star is very subtle, but it happens regularly, depending on how often the planet orbits around the star. The amount of light that gets blocked depends on the size of the planet and how much of the star it covers as it moves. Scientists can then detect this small and regular drop in light by carefully tracking the star over time. When they see this kind of pattern, where the star dims and brightens at consistent intervals, they know that something is causing it. That something is likely a planet passing in front of the star. By measuring how much the light dims, scientists can even learn about the size of the planet. Larger planets block more light, while smaller ones block less. The Kepler Space Telescope, which was launched by NASA, is one of the main tools used to find planets using this method. Kepler has been scanning the sky for years, watching the light from thousands of stars. Thanks to its observations, Kepler has discovered thousands of exoplanets that we would have never known about otherwise. Each of these planets is orbiting its own star, many in distant parts of our galaxy. By using the transit method, scientists are not only finding new planets, but also gaining valuable information about them, such as how long it takes for the planet to complete its orbit, and whether the planet might be in the habitable zone, a region around a star where conditions could be right for life. This method is so effective that it has led to some of the most exciting discoveries in the search for life beyond Earth. When a planet's transit is detected, scientists can follow up with other instruments to learn even more, like whether the planet has an atmosphere or if it's made of rock, gas, or ice. Every time a planet passes in front of its star, it gives scientists a clue that leads to the discovery of new, distant worlds. The radial velocity method, also known as the Wobble method, is a fascinating way scientists find planets that are far away from us, even when we can't see them directly. Here's how it works. When a planet orbits around a star, its gravity pulls on the star ever so slightly. Think of it like a tug of war. While the planet is moving in its orbit, it exerts a small force on the star, causing the star to move, or wobble, just a little bit. Now this wobble is incredibly small, so small that you wouldn't notice it with the naked eye, but it's there. Stars are massive, but they don't just stay in one place. Even though they appear to be stationary, they're actually moving in response to the planets orbiting around them. This movement is due to the gravitational pull the planet exerts as it moves in its orbit. So, while a planet is pulling on the star is moving in a tiny circle, or ellipse in response to this pull. To detect this wobble, scientists use very sensitive instruments that can measure the star's movement with extraordinary precision. By observing the star's position in the sky and tracking how its light shifts, they can detect the tiniest wobble caused by an unseen planet. These shifts in light happen because of something called the Doppler effect. This effect is the same reason why a car engine's sound changes as it drives past you. When the star moves toward us, the light gets slightly bluer, a shift to shorter wavelengths. When it moves away, the light becomes redder, a shift to longer wavelengths. By measuring these small colour shifts, scientists can tell if a planet is tugging on the star. Now imagine trying to detect a planet that is millions or even billions of light years away. Without seeing the planet itself, the Wobble method allows scientists to know it's there. This method works for planets that might be too far to see directly, or even planets that are too faint compared to their stars to spot through a telescope. The beauty of the radial velocity method is that it lets us learn about planets that we wouldn't be able to detect otherwise. We can figure out things like the planet's mass, how far it is from its star, and sometimes even how strong the gravitational pull between the two is. It's like uncovering hidden information about a planet without ever seeing it. This method has been crucial in finding many exoplanets, planets that orbit stars outside our solar system. In fact, it has helped astronomers discover hundreds, if not thousands, of planets we didn't know existed. And the best part? It opens up a window into the vast, mysterious universe, giving us clues about other worlds that might one day be explored. The radial velocity method allows scientists to detect hidden planets by measuring how their gravity causes their stars to wobble. The direct imaging method is an exciting and rare technique that allows scientists to capture real pictures of exoplanets. Exoplanets are planets that exist outside of our solar system, orbiting stars far away. But here's the challenge. Stars are incredibly bright, and their light can make it nearly impossible to see the faint and distant planets orbiting them. It's like trying to spot a tiny dim light in the middle of a huge spotlight. To overcome this problem, scientists use highly advanced telescopes that have special technology. This technology is designed to block out the overwhelming light from the star, allowing the telescope to focus on the much dimmer exoplanet. It's almost like using a pair of special glasses that help you see the faintest details in the dark, even with a blinding light in the background. While this method is not something scientists can do every day, it is incredibly valuable when it works. It provides the rare opportunity to directly observe exoplanets, helping us understand their size, atmosphere, and even the conditions on their surface. With these images, researchers can learn more about whether these exoplanets could support life, or if they have any similar features to the planets in our own solar system. Direct imaging allows scientists to take a snapshot of distant worlds, bringing us closer to understanding the vast and mysterious universe around us. The gravitational microlensing method is a fascinating and powerful technique used by astronomers to find planets in space that would be impossible to detect using traditional methods. To understand how it works, let's break it down. Imagine a planet drifting in the vastness of space. Now picture a distant star shining light billions of miles away. Normally, the star's light travels straight toward us. But if the planet happens to pass directly in front of that star, something incredible happens. The gravity of the planet acts like a magnifying glass, bending the light from the star in a way that makes the star appear brighter and bigger than it really is. This bending of light occurs because gravity has a unique ability to warp the space around it, according to Einstein's theory of relativity. The more massive an object, like a planet or a star, the stronger its gravitational pull. When the planet moves in front of a distant star, its gravity distorts the star's light path. This phenomenon creates a temporary and noticeable brightening effect, which is what we call microlensing. What makes this method so special is that it can reveal planets that we can't see with regular telescopes. These planets could be far away, in places where no light is coming directly from them. Typically, detecting a planet involves spotting the light they reflect or detecting the small gravitational pull they exert on their parent star. But in some cases, these methods don't work, especially if the planet is too small or too far from its star. However, with gravitational microlensing, even the smallest and most distant planets can be detected as long as they pass in front of a star. This rare event is a bit like finding a hidden treasure in space. The moment the planet's gravity bends the light, scientists on Earth can use special instruments to measure the change in the light's brightness. They can then study this change to figure out details about the planet, like its size, location, and even how far it is from its star. Gravitational microlensing is not only a way to detect planets, but it also helps scientists study other objects in space, like black holes or other strange cosmic phenomena that could also cause similar light bending. Because the planets detected this way are often in faraway parts of the universe, the method opens up an entirely new way to explore and understand space, allowing astronomers to discover things they couldn't have dreamed of just a few decades ago. Astronomers have discovered a number of exoplanets that might be capable of supporting life, and each one has unique characteristics that make them fascinating to study. Some of the most exciting of these planets include Proxima b. This planet orbits Proxima Centauri, the closest star to our solar system, located just over 4 light-years away. Proxima b is situated within the habitable zone, an area where conditions might be right for liquid water to exist on its surface. While this is a hopeful sign, scientists are still investigating whether the planet has a protective atmosphere that could make it possible to sustain life. TRAPPIST-1 system. A remarkable star system located about 40 light-years away, it contains 7 planets roughly the size of Earth. 3 of these planets are in the habitable zone, where temperatures could allow liquid water to exist. This makes TRAPPIST-1 one of the most promising systems for the search for alien life, with scientists paying close attention to its potential. Kepler 442b, known as a super-Earth, Kepler 442b is a planet that lies within the habitable zone of its star. It's around 1,200 light-years away, but it's considered one of the best candidates for habitability. Its size and location suggest that it might have the right conditions, such as the right temperature and an atmosphere for life to thrive. LHS 1140b, a rocky planet about 40 light-years away, LHS 1140b is another exciting find. It's believed to have a thick atmosphere and possibly even liquid water, making it an excellent candidate for scientists who are looking for signs of a life beyond our solar system. Its rocky surface also suggests it could have Earth-like conditions. These planets are just a few examples of the many exoplanets scientists are studying. Each discovery brings us closer to understanding whether life could exist elsewhere in the universe, making these distant worlds incredibly intriguing. With powerful telescopes like the James Webb Space Telescope, JWST, scientists now have an incredible tool to explore the atmospheres of planets outside our solar system, known as exoplanets. They carefully examine these distant worlds, searching for specific gases, such as oxygen, methane, and carbon dioxide. These gases are important because on Earth they're closely linked to life. For example, oxygen comes from plants, methane is often produced by living organisms, and carbon dioxide is a key part of the cycle of life. Even though scientists haven't yet found direct proof of alien life, the discovery of thousands of planets that could potentially support life has made the search more exciting than ever. The sheer number of these planets suggests that life might not be unique to Earth. Somewhere out there, in the vastness of the universe, another world might be teeming with life, waiting to be discovered. A rogue planet, sometimes called a free-floating planet or an isolated planetary mass object, is a large space object that looks and behaves like a planet. But unlike most planets, it doesn't go around any star. Instead, It drifts alone through the cold, dark stretches of space, not tied to the gravity of a star like Earth is to the Sun. That's why they're often called rogue. They're wanderers, out on their own. These lonely worlds can come from many different places. Some of them are born inside regular planetary systems, just like Earth or Jupiter. But something happens, maybe a collision, a close encounter with another planet, or a powerful gravitational push, and they get kicked out of their home systems. Once ejected, they drift away into the galaxy, no longer bound to their star. Other rogue planets might never have had a star to begin with. They could have formed by themselves in the empty regions of space, far from any light or warmth. The Milky Way galaxy, where our solar system lives, might be filled with billions or even trillions of these mysterious worlds. And upcoming space missions, like the Nancy Grace Roman Space Telescope, will help scientists find more of them and understand how many are out there. Interestingly, some of these objects may not be planets at all, at least not in the way we usually think. Some might have formed more like tiny stars, just not big enough to start shining like real ones. The International Astronomical Union has suggested calling these objects sub-brown dwarfs, a name used for star-like bodies that never got hot enough to ignite and shine. One strange object scientists discovered might be a good example of this. It could have either been thrown out of a star system or formed all on its own as a sub-brown dwarf. Over the years, scientists have used several different names for these strange bodies. Early on, researchers talked about isolated planetary mass objects and free-floating planets. These technical terms are still used in many scientific papers, but in studies about a special technique called microlensing, the simpler name rogue planet has become more common. The media and press often use terms like wandering planet, starless planet, or free-floating planet as well. For example, in the year 2021, press releases describing the discovery of more than 70 rogue planets used several different names to help explain what they were. The first big discoveries of these isolated planets happened around the year 2000. A team from the United Kingdom, led by Lucas and Roche, found some of these objects using the Ucurt telescope in the Orion Nebula. That same year, another team from Spain, led by Zapatero Osorio, found similar objects in a star cluster called Sigma Orionis, using the Keck telescope. Their findings were confirmed in the year 2001 using a method called spectroscopy, which helps determine what something is made of by analysing its light. These were important breakthroughs and are now seen as major milestones in the search for rogue planets. Even earlier, in 1999, a Japanese team led by OISA found potential rogue objects in the Shamalian Bean cloud, but their discovery wasn't fully confirmed until 2004, when a team from the United States used spectroscopy to prove they were real. There are two main ways to find planets that don't orbit any star. One method is called microlensing, and the other is direct imaging. Microlensing is a clever trick based on gravity. When a planet passes in front of a distant star, its gravity bends the light from that star, making it appear briefly brighter. In 2011, Takahiro Sumi, an astrophysicist at Osaka University in Japan, led a study with help from two major collaborations, the microlensing observations in astrophysics and the optical gravitational lensing experiment. They used telescopes in New Zealand and Chile to watch more than 50 million stars in the Milky Way. The telescopes they used were the 1.8-metre M002 telescope at Mount John Observatory in New Zealand and the 1.3-metre University of Warsaw telescope at Las Campanas Observatory in Chile. They recorded 474 microlensing events, moments when gravity bent starlight. Out of these, 10 were short and sharp enough to suggest they were caused by planet-sized objects, each about the size of Jupiter, but with no nearby star. From this, the team estimated that for every star in our galaxy, there could be almost 2 rogue planets the size of Jupiter. Another study went even further, proposing there might be 100,000 times more rogue planets than stars, although this larger number includes tiny objects far smaller than Jupiter. In 2017, Przemek Mróz from the Warsaw University Observatory led a new study that was 6 times bigger than the earlier one. This study suggested that for every star in the Milky Way, there might be no more than 1/4 of a Jupiter-sized rogue planet. Then came a groundbreaking discovery in September 2020. For the first time ever, scientists used microlensing to detect a rogue planet with the mass of Earth. It was called OGLE 2016 BLG 1928. This was a major moment, showing that even Earth-sized rogue planets are out there, completely alone. But microlensing, while powerful, has its limits. It can tell us how big a planet is, but it can't show us what it looks like or tell us much about its surface or atmosphere. That's where direct imaging comes in. Direct imaging means actually taking pictures of these lonely worlds. It's challenging because they're so faint and far away, but it can reveal more details. To figure out the mass of a rogue object, scientists need to know how bright it is and how old it is, and figuring out the age of something so distant isn't easy. Many of the rogue planets found so far are in young star-forming regions, places in space where new stars and planets are being born. These areas are well known, and their age is easier to estimate. Most of these planets are less than 200 million years old and are quite large, more than 5 times the mass of Jupiter. They often belong to types of brown dwarfs known as L dwarfs and T dwarfs. A few are even older and colder, Y dwarfs, which can have masses between 8 and 20 times that of Jupiter. One of the closest rogue planet candidates is WISE 0855-0714, which is only about 7.27 light-years away. These cold, faint objects give scientists a rare chance to study rogue planets up close. But to really understand them, we need better ways to measure their brightness, age, and motion. The first of these isolated planetary mass objects was spotted in the early 2000s, especially in young regions where stars were forming. Some of them might have formed like stars, slowly gathering gas and dust until they became sub-brown dwarfs. Others, however, may have formed like planets but were thrown out of their systems. These would move differently than the ones that stayed in their birthplaces. They would also lack the dust disks found around many young objects and may contain more heavy elements, or metals. For example, an older object called WISE-J 0830+2837 is moving extremely fast, about 100 kilometers per second, which could mean it was kicked out of its home system. Another one, WISE 1534-1043, moves even faster, around 200 kilometers per second. This speed raised the possibility that it might be a rogue planet, but its colour shows it's probably an old brown dwarf instead. Right now, scientists believe that most of these strange objects are at the very lowest end of the star formation process. Not quite stars, not quite regular planets. But their true origins are still unknown. As telescopes become more powerful and technology improves, astronomers hope to unlock more secrets about these wandering worlds and better understand how they fit into the story of how our galaxy formed and evolved. Most rogue planets are extremely cold because they don't have a star to keep them warm like the planets in our solar system do. However, even though these planets are freezing, they still give off a small amount of heat. This heat can't be seen with the human eye, but it can be noticed through a special kind of light called infrared radiation. Infrared radiation is like the heat you feel when you stand near something warm, even though you can't see it. To find these wandering planets, scientists use very advanced space telescopes like NASA's James Webb Space Telescope. These telescopes are made to catch that faint hidden heat in the form of infrared radiation. The James Webb Space Telescope is one of the most powerful tools we have for learning about the universe. Unlike normal telescopes that mainly see visible light, the light our eyes can see, the James Webb can see infrared light, which lets it look through thick clouds of gas and dust in space and find things that would normally stay hidden. By scanning the huge sky for signs of infrared light, scientists can find rogue planets that are far away from any star. These planets are often lost in the cold, dark parts of space, so spotting their faint glow is a big challenge. But with help from the James Webb Space Telescope, which is much more sensitive than older telescopes, scientists can now find these strange planets that drift through the universe with no set path. Some planets in our solar system, like Jupiter, are known to give off strong radio waves. This happens because of their strong magnetic fields. Magnetic fields are invisible forces that surround a planet, and they can affect tiny particles in space like electrons. When these particles move through the magnetic field, they can make radio waves, which are a kind of energy that travels through space in the form of waves. Jupiter's magnetic field is one of the strongest in our solar system, much stronger than Earth's. In fact, Jupiter's magnetic field is so strong that it traps powerful particles from the Sun, and these particles spin around the planet. As they move through the magnetic field, they make radio waves, which we can pick up using special tools called radio telescopes. These radio waves are often so strong that scientists can hear them from Earth, even though Jupiter is millions of miles away. But it's not only planets like Jupiter that can make these radio waves. Scientists think that rogue planets that don't go around a star and instead drift through deep space, might also give off radio waves. Since rogue planets don't have a star to light them up or keep them warm, they are much harder to find with the usual tools that look for visible light. But if rogue planets have magnetic fields, they could still give off radio waves, just like Jupiter does. Special radio telescopes, which are made to catch these radio waves, could be used to find rogue planets floating through the endless space. These telescopes are very sensitive and can pick up even the weakest signals from faraway objects. The signals from a rogue planet's magnetic field might be small, but with the right tools, scientists might be able to find them. In fact, radio waves from these planets could help us discover things we can't see with regular telescopes. One of the most exciting things about this is that it gives us a brand new way to find planets. Right now, most planets are found by the light they shine or by the way they affect light from nearby stars. But finding radio waves could give us a completely new way to find planets, even ones that don't go around stars at all. This might help us find many more planets in our galaxy and help us understand how planets are made, what they are made of, and how they can stay alive in space without a star. Also, this new way of studying could help us learn more about how magnetic fields work in space. We already know that magnetic fields help protect planets from the Sun's harmful rays, acting like a shield. By learning more about the magnetic fields of rogue planets, scientists could understand how these fields protect planets and what makes them strong or weak. This could give us important clues about the kind of conditions needed for life to survive, even on planets without stars. If planets can be pushed out of their solar systems, it makes sense that their moons could be pushed out too. Picture a planet being thrown out of its home in space, with its moons still travelling with it through the universe. While this may sound like a wild idea, it's actually possible. Some moons might stay with their planets as they float through space, continuing their journey together, even though they no longer belong to a solar system. But what about the moons that don't stay? Sometimes, the pulling forces from other huge things in space, like nearby stars or other planets, can tug on a moon. This pull can be so strong that it breaks the connection between the moon and its planet, sending the moon off on its own path. When this happens, the moon becomes a rogue, meaning it doesn't orbit any planet. It floats alone through space, with nothing to circle around. A rogue moon, unlike a rogue planet, is much harder to find. That's because moons are usually much smaller and don't shine with their own light like stars or some planets. Since they don't give off light, they're almost invisible to our eyes or even to most telescopes, unless they're near something bright. That makes them really hard to spot, so finding one would be an even bigger challenge for space scientists. Still, if rogue moons really do exist, they could help us understand a lot about how planet systems are made and how they fall apart. The fact that a moon can be separated from its planet and float away shows that the universe is a much wilder and more active place than we might think. It proves that everything in space, no matter how big or small, is affected by the things around it. And sometimes this creates surprising changes, like moons being pulled away from their planets. In a way, rogue moons could be the universe's forgotten travelers, silently floating through space, holding secrets about the wild and surprising nature of our galaxy. Finding just one of them, or even a group of them, would open a brand new chapter in how we understand space. Even though rogue planets don't go around stars, they are still very interesting and important for scientists to study. At first, it might seem impossible that a planet floating alone in cold, dark space, without any warmth or light from a star, could have life. But scientists believe that if the conditions are just right, life might still survive on a rogue planet. For example, if a rogue planet has a thick atmosphere, it could trap heat from inside the planet, kind of like warmth from the planet's core. This might keep the surface warm enough for liquid water, which is needed for life to exist. Some rogue planets might even have huge oceans hidden under their surfaces, kind of like the ones found on moons such as Europa and Enceladus, which go around Jupiter and Saturn. These oceans might be warm and safe places where life could survive, even far away from the light of any star. By studying rogue planets, scientists can learn a lot about how planets are made and how they change over time. If many planets are thrown out of their solar systems, it shows that making planets is a much messier and more random process than we once believed. This could change the way we think about how stars and planets are born and how they die. One of the biggest mysteries in the universe is dark matter, an invisible thing that makes up a big part of the universe's mass but can't be found using regular tools. Some scientists think that rogue planets might help us solve this mystery. Because they are so massive, these wandering planets can bend the light from faraway stars, which is a strange effect called gravitational lensing. In the year 2021, scientists made an amazing discovery when they saw a rogue planet about the same size as Jupiter, travelling freely through the Milky Way galaxy, far away from any star. This planet was all by itself, giving scientists a rare chance to study one of these mysterious worlds. Then, in the year 2023, scientists found clues that rogue planets might actually be more common than stars in the universe. This surprising idea changes what we used to think about how planets are made and how they live in space. Looking to the future, exciting space missions like NASA's Nancy Grace Roman Space Telescope are on the way. These missions are expected to find even more rogue planets, and they might change how we see the universe in the next few decades. With powerful new tools and amazing discoveries just around the corner, the mystery of these wandering worlds continues to inspire both scientists and space lovers everywhere. One of the most mind-blowing mysteries in the entire universe is something we can't even see: dark matter. It's like an invisible thread that holds the universe together, creating a vast, unseen web across the cosmos. We can't look at it with our eyes, and even the most powerful telescopes can't spot it. But scientists are sure it's there, not because they can see it directly, but because of the strange and powerful ways it affects everything around it. When astronomers watch galaxies spinning in space, they notice something strange. These galaxies are turning so fast that based on the visible stars and gas inside them, they should be flying apart. But they don't. Something unseen is holding them together. That something is dark matter, a hidden force with an enormous pull, helping to shape the universe from the shadows. Unlike regular matter, which shines like stars or reflects light like the moon, dark matter doesn't shine, reflect, or absorb light. It's completely invisible. That's why it's called dark, not because it's spooky or shadowy, but because we simply can't see it. Yet even though we can't detect it with our eyes, we can still see the effects of its gravity. It's like trying to figure out the shape of the wind by watching the trees move. Now here's the really surprising part. Everything we can actually see, stars, planets, dust, gas, and even people, makes up only about 5% of the entire universe. That means all the beautiful galaxies and glowing nebulae we admire in space photos are just a tiny part of what's really out there. A much larger chunk, roughly 27%, is made of dark matter, and the biggest part of all, about 68%, is something even stranger, called dark energy. While dark matter pulls things together, dark energy pushes them apart, stretching the universe faster and faster as time goes on. So, in the grand story of the universe, most of what exists is completely invisible to us. But these invisible forces, dark matter and dark energy, are the real architects of the cosmos. They've been shaping everything from the tiniest atoms to the biggest galaxy clusters for over 13 billion years, ever since the universe began. To truly understand why dark matter is so important, we need to go back, way back, to the very beginning, just after the Big Bang, which happened nearly 13.8 billion years ago. In those early moments, the universe was a hot, chaotic soup of particles and energy, buzzing and boiling with intensity. But even then, dark matter was already there, quietly shaping things. As the universe expanded and cooled, dark matter started to gather in clumps. Even though it was invisible, it had gravity, and that gravity began pulling regular matter like gas and dust toward it. This helped form the first stars and galaxies. You could think of dark matter like an invisible blueprint that guided the way the universe grew. Without it, galaxies might never have formed, and the universe would be an empty, scattered place. One of the most amazing discoveries about dark matter is the idea of dark matter halos. These are enormous invisible clouds of dark matter that surround entire galaxies. Imagine a galaxy like our Milky Way floating inside a giant bubble made of dark matter. These halos help keep galaxies stable, stopping them from flying apart as they spin. Scientists believe every galaxy is wrapped in a halo like this. Without these halos, galaxies wouldn't stay together and might not even exist at all. But how do scientists know dark matter is there if they can't see it? One powerful clue comes from a technique called gravitational lensing. This happens when light from faraway galaxies gets bent by the gravity of something really massive, like a galaxy cluster. It's like a cosmic magnifying glass. When scientists study how this light bends, they realize there's more mass present than we can see. Something invisible must be adding extra gravity. That extra mass is dark matter. Gravitational lensing is one of the strongest pieces of evidence that dark matter is real. It shows that there's way more mass in the universe than meets the eye. It paints a clearer picture of how dark matter is spread across space, revealing huge amounts of it hidden within galaxy clusters. Another key clue comes from something called the cosmic microwave background, or CMB. This is a faint glow of radiation left over from the Big Bang. It's like a snapshot of the baby universe, taken when it was just about 380,000 years old. When scientists examine tiny patterns in the CMB, they can tell that dark matter was already present back then, helping to form the first galaxies. Right now, scientists are on an exciting mission to find out what dark matter is really made of. One leading idea is that dark matter is made of mysterious particles called WIMPs, short for weakly interacting massive particles. These particles are believed to barely interact with normal matter, which makes them extremely hard to detect. But scientists haven't given up. They're using giant underground detectors, powerful particle smashers like the Large Hadron Collider, and even space-based instruments to try and catch a glimpse of these elusive particles. Even though no one has directly detected dark matter yet, every experiment, every test, and every failed attempt brings scientists a little closer to the truth. Even the tiniest breakthrough could open the door to a brand new understanding of the universe, and the story doesn't end there. New space missions like the James Webb Space Telescope are giving scientists a deeper look into the distant past. These telescopes are letting us see galaxies as they were billions of years ago, closer to the time when dark matter first shaped them. On Earth, engineers are building even more sensitive detectors to try and spot dark matter particles. Some of these devices are placed deep underground, far away from other radiation, just to catch the faintest hint of dark matter's presence. All of this is leading toward a huge goal: to finally understand this invisible substance that holds the universe together. It's not just about solving a mystery, it's about rewriting the story of how everything began, how it grew, and what the future might hold. Dark matter may be hidden from sight, but it has been guiding the universe since the very beginning. As scientists continue their search, we stand on the edge of discoveries that could change our understanding of space, time, and everything in between. The journey is far from over. In fact, it's only just beginning. Dark energy is one of the biggest mysteries in the entire universe. It's strange, puzzling, and incredibly important. Scientists have been trying to figure it out for many, many years, but even now they still don't fully understand what it is. What we do know is that dark energy takes up most of the universe, about 68% of it. Imagine the universe is a huge pie. The biggest piece by far is dark energy, yet we can't see it, touch it, or directly measure it. It's completely invisible. The only reason we even know it's there is because of how it affects the things we can see. To understand this better, think about standing in a room while someone gives you a push from behind. You don't see who it is, but you definitely feel the force. That's a lot like dark energy. It's pushing the universe, but we can't see where the push is coming from. The story of dark energy really began in the late 1990s. Two different groups of scientists working separately made a surprising discovery that changed our understanding of the universe. They were studying supernovae, huge explosions that happen when certain stars die. These explosions are very bright, and since their brightness stays consistent, scientists use them like cosmic yardsticks to measure distances in space. But when the scientists looked at these supernovae, they found something shocking. The explosions were farther away than they had expected. This meant that the universe wasn't just expanding, it was expanding faster and faster. That was completely unexpected. The only way to explain this strange acceleration was to suggest that some mysterious force, dark energy, was pushing everything apart. This was a game changer. Before this, scientists believed gravity was the main force shaping the universe. Gravity pulls things together, but dark energy seemed to be doing the opposite, pushing everything apart. So, what is dark energy? That's the big question. To answer it, we have to understand that space itself is not just empty nothingness. Think of space like a stretchy fabric. This fabric can grow, and as it stretches, everything in it moves farther apart. That's what scientists mean when they talk about the expansion of the universe. Now imagine that something is pulling on that fabric from all sides, making it stretch faster and faster. That's what dark energy seems to be doing. A good way to picture this is to think of a balloon being blown up. As the balloon inflates, points on its surface move farther and farther away from one another. In this picture, the galaxies are like those points. They aren't flying through space by themselves. Space itself is growing and carrying them apart. But here's the really weird part. Dark energy doesn't behave like any of the other forces we know. Gravity pulls things together, electricity makes opposite charges attract. But dark energy pushes things apart, and even stranger, this pushing force seems to be getting stronger as time goes on. Scientists have come up with several ideas to try to explain dark energy. One idea goes back to Albert Einstein. In the early 1900s, he added something to his famous equations called the cosmological constant. At the time, he thought the universe was not expanding or shrinking, so he used this constant to balance things out. Later, when he found out the universe was expanding, he called it his biggest mistake. But after the discovery of dark energy in the 1990s, scientists brought this idea back. In this theory, dark energy is a constant force that fills all of space evenly and never changes. It's like an invisible energy field spread throughout the entire universe. Another idea is called quintessence. This theory suggests that dark energy might not be constant. Instead, it could be something that changes over time and space. Imagine a kind of cosmic energy fluid flowing through the universe, sometimes stronger, sometimes weaker. This energy might act more like a magnetic field, always shifting and evolving. Some scientists think dark energy could have something to do with extra dimensions. We live in a world with 3 dimensions of space, up and down, left and right, forward and backward, and one of time. But what if there are more dimensions out there that we just can't see? These hidden dimensions might be affecting the universe in ways we don't understand, and dark energy could be the result of how those dimensions interact with our own. There's also a different idea that maybe dark energy isn't a separate force at all. Maybe the real issue is that we don't fully understand how gravity works, especially when we look at really huge distances. Some scientists believe that gravity might act differently across the vastness of space than it does here on Earth. If that's true, then what looks like dark energy might just be the result of our limited understanding of gravity on a cosmic scale. Even though dark energy is so mysterious, scientists have found some clever ways to study it. One of the most important tools is watching supernovae and faraway galaxies. By measuring their light and how far away they are, scientists can figure out how fast the universe is expanding. This was how dark energy was first discovered back in the late 1990s. Another way is by looking at the cosmic microwave background, a faint glow left over from the Big Bang. This ancient light contains tiny patterns that give clues about the early universe. By studying these patterns, scientists can learn how dark energy might have influenced the shape and growth of the universe over time. There are also big projects underway to learn more. One of them is called the Dark Energy Survey, DES. In this project, scientists are using powerful telescopes to look at billions of galaxies and measure how dark energy is changing the universe. Another mission, called Euclid, was launched by the European Space Agency. This spacecraft will take detailed measurements of the sizes, shapes and positions of galaxies across the universe. By doing this, scientists hope to find new clues about what dark energy really is and how it works. One of the most mind-blowing and exciting things about dark energy is how it might affect the future of the entire universe. Dark energy isn't just something far away or mysterious, it's actually playing a huge role in what might happen billions of years from now. Scientists have discovered that dark energy is pushing the universe to expand faster and faster over time. And if this strange force keeps working the way it is now, it could lead to some truly dramatic changes in the very distant future. Imagine a time many billions of years from now when dark energy becomes so powerful that it stretches everything in the universe apart. This idea is called the Big Rip. In this wild scenario, the universe would expand so rapidly that galaxies would be torn away from each other. Then, individual stars would be pulled apart. Even planets and moons wouldn't be safe. Eventually, the force could become so extreme that even atoms, the tiny building blocks of everything, might be ripped apart too. It sounds like science fiction, but some scientists think this could really happen if dark energy keeps getting stronger. But there's also another possibility. What if dark energy isn't permanent? What if, over time, it weakens and loses its grip? If that happens, the universe might stop expanding. It could even start to shrink. This could lead to what scientists call the Big Crunch. In this version of the future, all the galaxies, stars and planets would slowly come back together, as if the universe were rewinding itself. Everything might collapse into a single, incredibly hot and dense point, just like how the universe may have started with the Big Bang. Right now, no one knows for sure which path the universe will take. That's because dark energy is still a huge mystery. We've only just begun to understand it. Scientists know it exists because they can see how it affects the way galaxies move and how fast the universe is growing. But we still don't know what it actually is. We can't see it, we can't touch it, and we can't measure it directly. It's like an invisible force that's hiding in plain sight. What we do know is this: dark energy is one of the greatest mysteries in all of science. It makes up most of the universe, around 70% of it. That means most of the cosmos is something we don't fully understand. It might be a constant, unchanging energy that fills all of space. Or it could be something that changes over time, like a living, moving force. Some scientists even wonder if dark energy has something to do with hidden dimensions of space that we can't see. Whatever it is, dark energy is a big piece of the puzzle when it comes to understanding how the universe works and where it's headed. As our telescopes get better, and as our science grows, we might finally uncover the secrets of this invisible force. And when we do, we'll be one step closer to understanding the ultimate fate of the universe itself.